few minutes.
Yeah, sure.
Okay.
All right, good morning. So welcome back to the last day of the meeting. And the first speaker of this morning will be Dennis Nestor from Vienna. He will talk about unramified chromophyton and Kupa-Kuma-Papa invariant.
Yeah, thank you very much for the introduction. And yeah, thank you very much for the invitation and for the opportunity to speak. And it's, of course, a pleasure to speak of this in front of this audience, especially in light of the fact that half of the names in my title are currently present in the audience. And so the title of the talk is Unramified Gromov-Witten and Kupa-Kuma-Papa invariance. And this is a talk about mathematical definitions. More specifically, it's about how one can give a direct algebra geometric construction of Kupa-Kuma-Papa invariance using unramified Gromov-Witten invariance, at least for a large class of geometries. And so, the brief plan of the talk is as follows. So hopefully I'll start with a gentle introduction to unramified Gromov-Witten and Kupa-Kuma-Papa invariance. And then I'll talk about a certain wall-crossing phenomena in Gromov-Witten theory. And using this wall-crossing phenomena, we can actually prove that unramified Gromov-Witten invariance and Kupa-Kuma-Papa invariance are equal for in Fano and primitive Calabi-Yau cases. I'll explain what it means later. And then the final part of the talk is about how this wall-crossing fits into a bigger picture. I mean, some of you seeing the word wall-crossing probably think about wall-crossing in triangulated categories in the context of Donaldson-Thomas theory, but this is a completely different phenomenon. And in fact, only recently it became possible to talk about this phenomenon as something general that holds in many different contexts. Well, for example, it holds in context of unramified Gromov-Witten theory, then it holds also in quasi-map theory, holds in Landau-Ginzburg models, then Donaldson-Thomas theory, Hurwitz theory, and so on and so forth. So let me start with introduction. So, I mean, the best way to introduce unramified Gromov-Witten invariance and Kupa-Kuma-Papa invariance is to talk about the standard Gromov-Witten invariance. So, for the most part of the talk, X will be just a smooth projective complex threefold, and to X, you can associate what's called a space of stable maps from nodal curves of genus G and markings in the class beta. So in other words, this is just holomorphic maps from Riemann surfaces with possibly nodal singularities. And there are a bunch of n points, regular smooth points, distinct smooth points. The stability just refers to the fact that the automorphisms of these maps are finite, and we identify all the all the maps by automorphisms. Then for a bunch of classes on X, we can define so-called Gromov-Witten invariants. So we use these evaluation maps. So evaluation maps, they just send a map F to the image of a marking Pi, and then we pull back classes from X and integrate on the space MGN X beta. I mean, there are several ways of making sense of this integration. You can use either algebraic geometry or symplectic geometry. I'll not talk about it in details, but I'll just say that I will be always in the realm of algebraic geometry. And so, I mean, in physics, these invariants, I mean, these are just correlators of a twisted A model, but algebraic geometrists want to interpret these numbers as counts of curves of genus G in the class beta passing through gamma i's. So gamma i's, you view them as some kind of submanifold, some loci in the target. And here's a picture, so you have this nice nodal curve mapping to X, and then you count how many of them pass through this loci defined by gamma i's. But already from this picture, you can see there is a problem with this interpretation. So what is the problem? The problem is that in the space of stable maps, there will be contracted components. So there will be maps from irreducible curves, such that one of the components of that curve is contracted to a point. So we call it contracted components. And then there will be so-called multiple covers. So there will be maps from curves such that it's maps to degree d to 1 on its image. So we call that multiple covers. And so what it means, the presence of this kind of maps in the space of stable maps, geometrically it will lead to overcounts in Gromov invariants. So in other words, lower genus counts actually contribute to higher genus counts. So for example, if you look at this picture, well, it's clear that, we don't count genus 4 curves, we count genus 3 curves because one of the genus is just being contracted to a point. And moreover, since we identify our maps by automorphisms, the invariants that we get are actually rational numbers, but not integers. So what is the solution to the problem? Well, solution for Claudel threefolds that came from the paper of Gapakumov-Waffa. And in most basic terms, they gave us the following recipe to clean up our Gromov invariants from these multiple covers and contracted components. So we do the following. Firstly, in the case of Calabi-Yau threefold, you don't have to put any insertions. So that's what this empty sign means. You just can count curves on the nose. If we put them, so we put this Gromov invariants in the generating series. There are two parameters. One of them keeps track of the degree. Another one keeps track of the genus. And then we just do the following formal manipulation with the generating series. We express it in terms of the sign functions. Well, the leading factor of the sign function is lambda. So this you can express any formal generating series with even powers of lambda in terms of the sign functions. And then you collect these coefficients in front over here, and that you declare to be Gapakumov-Waffa invariants. So this is indirect definition of Gapakumov-Waffa invariants in the sense that we use Gromov invariants to define them. And well, more often, these invariants are referred to as BPS invariants. They count BPS states. But in this particular case, in the context of Gromov theory and this formula, I'll refer to them as Gapakumov-Waffa invariants. Okay? Well, if you've never seen this formula, it might seem a bit arbitrary. In fact, you can perfectly explain it from a mathematical point of view, but before doing that, I'll just say that you can do the same thing, not for Calabi-Yau threefolds, but for Fano threefolds as well. So an example of Fano threefold is just a projective space. So you do the same, you just put the invariants in a generating series. In this case, you have to also do insertions. You need to insert gamma i's. In this case, it's simpler because, in fact, in the case of Fano, there are no multiple covers. There are only contracted components. So we don't have to sum over Q over the parameter that keeps track of the degree because curves in different degrees don't talk to each other in the case of Fano. And so you have the same formula. So you put it in generating series, and you then express it via the sign functions. And that was proposed by Pandaripanda. And you can actually verify easily that in a case if beta is not a multiple of another class, and it pairs trivially with a canonical class of X, these two formulas coincide. Okay. So let me talk about the properties of these invariants. And explain what the formula actually means. So firstly, these terms, the sign functions are actually responsible for contracted components. So their presence, in some sense, removes the contracted components from Gromov invariants. And there are Hodge integrals. I'll talk about the Hodge integrals on modular space of stable curves, and I'll talk about Hodge integrals a bit later as well. And then the summation over D. So let me just go back. You see we sum over D over here. So the summation over D is it takes care of multiple covers, and in fact it's if expressed correctly, expressed in language of Donaldson-Thomas theory, this is a plathistic exponential, and this is just a shadow of the fact that if we upgrade our invariants to some vector spaces whose signed dimension gives us the invariants, then the symmetric powers of the vector spaces associated to BPS invariants or Gapakumov invariants is naturally isomorphic to vector space that associated to Donaldson-Thomas invariants or equivalent to Gromov invariants. And then by works of symplectic geometers, well, there is a long sequence of works by Zinger, Yanel, Parker, Dawn, and Balpuski. I think the first one is from 2008 by Zinger, and the most recent one is actually from 2021. And so what we know from their works is that if we define Gapakuma-Buffer invariants like that, then they are integers, and they satisfy a finiteness property, which means that they vanish for a fixed class beta, they vanish for high genus. So it took, as you can see, it took mathematicians a very long time to prove these expected properties of Gapakuma-Buffer invariants, and mainly because we don't have also a direct definition of them. And so altogether, these facts, in some sense, they solve all the geometric problems of Gromov-Witten theory. So Gapakuma-Buffer invariants are, in some sense, from a geometric point of view, they are just as close as we can get to actual honest curve counts. And for example, this property, finiteness, is a particularly nice one because a priori, Gromov-Witten invariants, there are infinitely many of them for infinitely many genera in a fixed class. And so, but the complexity of this infinite Gromov-Witten invariants is actually captured by only finitely many Gapakuma-Buffer invariants. So yeah, but as I said, we gave an indirect definition construction of this Gapakuma-Buffer invariants using Gromov-Witten invariants, and a direct construction is very much desired. By direct construction, I mean that we want to construct a space of something such that if we integrate over it, we get Gapakuma-Buffer invariants. So let me talk about how can we actually approach this problem. So the most popular approach is, in fact, my mathematical approach is based on the work of the Gapakuma-Buffer themselves, and then there was the works of Hosono, Saito Takashi, Katz, and Kim Lee, and then the final sequence in this. The final work in this sequence was Maulik Toda's paper from 2016, and they proposed to define Gapakuma-Buffer invariants using the following geometry. So we take a space of one-dimensional sheaves on X, so you can view them as kind of curves with the vector bundles on them. So we want to count curves with the vector bundles on them, and then we want to get rid of the contributions that come from the deformations of vector bundles. So we want to retain only the information that is information of the support of this one-dimensional sheaf. So there is a Chow variety. The Chow variety is actually a space that parameterizes. So this is Chow X. This is a space that parameterizes embedded curves, but for some technical reasons, we cannot define integrals directly on those space. And so instead, we use these one-dimensional sheaves with this projection to Chow. So it just sends a sheaf to its support. So if we have this F, it sends it to C. And then we use this geometry. So we essentially use some kind of a virtual array filtration to get rid of the contributions that come from the deformations of sheaves. And in this way, we can define, hopefully, Gapakuma-Buffer invariants. Well, the definition works for any Calabi-Yau threefold. It's an agreement with the Gapakuma-Buffer approach. However, the problem with this definition is that, in fact, we don't know how to prove that the Maulik-Todas invariants are equal to Gapakuma-Buffer invariants. It can be verified in many situations, mainly in the case of local geometries. But then beyond that, it's extremely difficult to compute these invariants. If you didn't understand anything about this Maulik-Toda proposal, it doesn't matter because that's the only time I mention it, and I will not talk about this construction anymore. So let me talk about then another candidate for Gapakuma-Buffer invariants. And this is a proposal of Kim, Kresh, and Oh. So, it's called unramified Gromov-Witten theory. And the idea is very simple. So as I said, the difference between Gromov-Witten invariants and Gapakuma-Buffer invariants is contracted components and multiple covers. So why not just remove all of them? So multiple covers are difficult, but contracted components are in some sense much more geometric because you can remove them by the following condition. You just require that your maps are unramified. so their differential is non-zero at all points, or in other words, your map is a submersion. So in differential geometric terms, this is just a submersion. So let's consider just submersions from curves to our target. The difficult part is that you cannot just take a closure of such maps inside the space of stable maps. You will not be able to integrate over this space, and so we have to do something funky. So we have to, if you want to retain the condition of unramification, you have to actually allow your target to become degenerate. And so a general unramified map will look like that. So it will be a map from a nodal curve to a target X with the bubbles attached to it. So by bubbles, I will mean projective spaces of the same dimension. So the map is a submersion on all components, but the price that you pay for a space of such maps to be proper compact is that you have to introduce these bubbles on the target. If you know Grom-Witten theory, so in order to compactify Grom-Witten, I mean the space of stable maps, you have to introduce bubbles in a source, and so here we do the same but on the target. So let me make it a bit more precise. So I'll call Fulton-McPherson degeneration of X will be exactly X with these trees of projective spaces attached to it. I mean, you require that it's nodal, well, in the sense that you don't allow projective spaces to be attached, 3 or more projective spaces to be attached at the same point. But other than that, we consider all possible configurations of these projective spaces with trees of projective spaces attached to our fixed X. I mean, for the experts, this is what's called an iterated degeneration to a normal cone of a point. Divisors. But for the sake of explanation, I mean, you can imagine that as an attachment. You need to blow up, and then you attach. But you blow up a point, so roughly speaking. So in the dimension 1, if X was a curve, that's how it looks like on the nose, but in the high dimension, you're right, you have to blow up. So that's a Fulton-McPherson degeneration. And just like in the Grom-Witten theory, we can consider the space of unramified maps, not to X now, but to arbitrary Fulton-McPherson degeneration. So arbitrary X with the arbitrary configuration of these trees of projective spaces. You require now, I mean, what you gain from that is that you can require that maps are actually unramified, so there are submersions everywhere. You have to identify, well, you also require that they have finitely many automorphisms, but now you consider automorphisms up to, not only from the, I mean, you can consider automorphisms on the source and on the target. So all these bubbles, they have scaling and translation, and you consider the bubbles up to scaling and translation, and you then identify maps from your curves to Fulton-McPherson degenerations up to these automorphisms, both on the target and the source. And then you also require, I mean, just like in Grom-Witten theory, require it to be stable in the sense that there are only finitely many automorphisms. And in all ways, the spaces of unramified maps to these Fulton-McPherson degenerations is very similar to spaces of stable maps, meaning that they're compact and you can integrate over them. In case of X is dimension 1, this is actually something well known. This is just a compactified space of covers of a curve. Or in other words, it's a Hurwitz space. So Hurwitz space is just compactified space of covers of a curve. And so you might actually, you might say that, well, we actually complicated the problem. We removed the contracted components, but we introduced the bubbles. In fact, for miraculous reasons, introducing bubbles is a much better approach because, for example, in case of Hurwitz spaces are smooth and irreducible. There are smooth stacks, smooth Deligne-Mumford stacks, unlike spaces of stable maps. Spaces of stable maps to a curve actually have many irreducible components. They're very singular and so on and so forth. So in the case of a curve, if X is of dimension 1, that gives us a best possible compactification of maps from curves. So let me talk about the properties of this unramified Grom-Witten invariance. I mean, just like in the Grom-Witten invariance, yes. No, these Fulton-McPherson generations, they deform to each other. You can take an X, and you can actually degenerate X to X with these bubbles. So there will be, if you're referring to that, you're referring to the fact that the target is different. I mean, the target is not fixed, and so there are many.
Wondered, so the new moduli space you defined, is it?
Well, I mean, that's unclear, but because it's very complicated. Yeah, I don't know. It's virtually it's smooth. I mean, there is a notion of it has a perfect abstraction theory, just like stable maps. You don't know if moduli space of stable maps are connected, smooth, or reducible. I mean, they have very complicated deformation theory, but you know that they have a perfect abstraction theory, so you can view them from a perspective of derived algebraic geometry. You can view them as smooth moduli spaces. The fact that whether they're connected or not, it's actually not important for many purposes. Yeah, so you can define unramified Gromb-Witten invariants just like in a usual Gromb-Witten situation. You just pull back classes and integrate them over this space of unramified maps. And there are subtle differences between these unramified Gromb-Witten invariants and Gromb-Witten invariants. Well, firstly, Gromb-Witten invariants, you can package them in what's called the cohomological field theory. It's just a consequence of the fact that you can, you have gluing maps and they're compatible with the invariants. In the case of unramified Gromb-Witten theory, you cannot. It's not a cohomological field theory in the same way. Well, because in order to glue maps, you have to glue Fulton-McPherson generations as well. So, for example, just like Hurwitz theory, unramified Gromb-Witten theory in general is not a cohomological field theory. But it has a nice property. Because of unramification, you can always lift maps to Fulton-McPherson generations actually to the projectivization of a tangent bundle. Why is that? Because, well, all of our maps are submersions, so the differential is not zero, so you know where a tangent lines in your curve map to in a target. You have to make it a bit precise in the case when the target has bubbles, but you can do that. And so in particular, you can view, well, you can lift maps to the projectivization of a tangent bundle. So projectivization of tangent bundle parameterizes points with the tangential directions at those points. So you can always lift maps from Fulton-McPherson generations to these projectivizations of tangent bundles. And in particular, you can view unramified Gromb-Witten theory as a theory that lives actually over 5-dimensional complex manifold projective projectivization of a tangent bundle. It's a very useful perspective. In fact, I mean, it will be crucial for something later. In particular, if you take cohomology of a projectivization of a tangent bundle, it has more classes. So there is a hyperplane class, modulo some relations. So you can insert more classes. So in some sense, unramified Gromb-Witten theory is richer than a usual Gromb-Witten theory. And what's true is that if you actually pull back this hyperplane class, take a degree with respect to it. I mean, if you pull back a class, using this lift of a map from a Fulton-McPherson generation to projectivization of a tangent bundle, you pull back H, take the degree of it, it will be equal to 2G minus 2, and so it recovers a genus, and in some sense, a genus parameter in the unramified Gromb-Witten theory becomes a degree parameter. I mean, this facts will actually, these last three facts will be useful for computations. I don't know how to make sense of it how to put it in some kind of a bigger framework. I mean, I know that five complex dimensions appear in some papers and some considerations similar to, I mean, in which also Gopakon-Waffa invariants appear, but I don't know if it's part of that story. Okay, so that's the properties of unramified Gromb-Witten invariants. Let me go back to Gopakon-Waffa invariants. So as I said, I mean, when you use unramified Gromb-Witten invariants, you can only, at least in the form that I presented, we only removed contracted components. We didn't do anything for multiple covers. But I mean, it's already good enough for some purposes. In particular, there is a conjecture. The conjecture is the following. So if X is a funnel, so like a projective space, for example, or Calabi-Yau, and the class is not a multiple of another class, we call it a primitive class. then in fact unramified Gromov invariants are equal to Gapakumov invariants. Or in other words, if we use Gapakumov invariants using the formula that I presented before, well, this conjecture just states that if we put a Gromov invariance into a generating series like that, it's equal to unramified Gromov invariance up to this sine function over here. Okay? And so, I mean, one of the main theorems of the talk is that this conjecture is true. And more interestingly, in fact, this formula is a wall-crossing formula. So this guy over here is a wall-crossing formula. And unless you have any questions, I'll move to the second part of the talk about the wall-crossing. So where does the wall-crossing come from? And what does it mean, actually? So I'll explain now. I'll explain how we prove this theorem. So I'll explain how we show this identity, in particular how we prove that unramified Gromov invariants are equal to Gapakumov invariants using this wall-crossing technique. So where does the wall-crossing come from? Well, in fact, Gromov theory and unramified Gromov theory are, there is something in between. There are theories that live in between them. So we can define intermediate theories that interpolate between those two theories. And the way we do that, it's quite simple. I mean, it's not something super fancy. So we consider a map from nodal curves with the markings to arbitrary Fulton-McPherson degeneration, and then to each point of the Fulton-McPherson degeneration and each bubble of Fulton-McPherson degeneration. So bubble, when I say bubble, it just, let me go back. By bubbles, I'll always mean this projective space attached to X. So to each map from a nodal curve to W, we can to each point in W and to each bubble in W, we can associate what I call weights. So it's just some integer values. I'll denote them Wx and W projective space. I mean W bubble. And these weights, when they measure, when in case of a point, they measure how far a map is from being unramified over that point. And then in case of a bubble, in some sense, it measures how big the bubble is over this, I mean, how big the curve is over that bubble. I mean, I will not fully define how these weights, but for example, if you have a map and there is a contracted component, then it's clear that a weight should also account for, I mean, the weight should account for this contracted component. So in particular, weight, so if there is a contracted component, then the contracted component will contribute 2g minus 2 to the weight of that point. And the same happens if you have a bubble and then there is a curve of genus G over that bubble, so it will contribute 2g minus 2 to the weight of that bubble. Okay, and then we define the following thing. So it's for every epsilon, a positive real value, we say that a map is epsilon ramified if for all points in X, the weight of a point is less or equal to 1 over epsilon. And for all bubbles of that Fulton-McPherson generation, the weight of the bubbles is greater than 1 over epsilon. So 1 over epsilon is purely a convention, so you can just put also epsilon. And so here's the definition of epsilon ramified map. So what's so nice about it? So in some sense, it's a middle ground. I mean, it's something in between unramified and usual stable maps. And as we vary epsilon, we go from stable maps to unramified maps. So I'll say that more specifically. So firstly, let me define now a space of this epsilon ramified map. So for each epsilon, a real value, we define this space of epsilon unramified maps. So this is just maps that satisfy. So this is maps to all Fulton-McPherson degenerations, and then they satisfy the condition of being epsilon unramified. And then, well, we view this epsilon as a stability parameter. So each value of epsilon gives you a stability parameter, defines the stability of a map, and then it partitions the half line into walls and chambers. Chambers are those parts of the half-line where the space, moduli space of epsilon ramified maps is actually, yeah? Differential geometric terms? You can, in a case of a curve, is a branching divider. So you take you take the relative cotangent complex, and then you push it forward. It's going to be some complex, perfect complex in a target, supported on points, and you use that you use the thing to define this epsilon ramification. In high dimensions, it's a bit more complicated because the relative cotangent complex is supported on the entire thing, so it's not going to be supported on points. Yeah, or I mean, forget about relative cotangent complex, just relative cotangent bundle. I mean, you can use relative sheaf, relative cotangent sheaf to define this ramification. So yeah, so this epsilon. So what was I saying? So you have this moduli spaces of epsilon ramified maps, and so there is well, yeah. I mean, half real line is partitioned in chambers and walls. So inside chambers, this spaces are the same, and as you cross the wall, space suddenly changes like discontinuously. It's, well, actually walls, just by definition of our weights, I mean, there are integers. Of course, the walls will be just integers. But it's still useful to view this epsilon parameter as a continuous parameter. And so what's so nice about this epsilon unramified maps is that for small epsilon, you get back the space of stable maps. And for epsilon greater than 1, you actually get a space of unramified maps. So in particular, these spaces of epsilon unramified maps provide an interpolation between spaces of stable maps and spaces of unramified maps. I mean, it's easy to see. So if you use this definition of epsilon ramification, well, take epsilon very small. So if epsilon is very small, it says that ramification at all points can be arbitrarily large, but the weights of the bubbles, I mean, they have to be infinitely big. And if you take epsilon very small, by compactness, I mean, the bubbles cannot appear then in your moduli space. And similarly, if we take now epsilon large, if epsilon is large, you allow any bubbles, but because, I mean, that value becomes very small, and then, but you disallow all ramifications. In this way, you recover both spaces of stable maps and spaces of unramified maps. So here's a picture. So you have this two extremal behaviors. One of them is Gromb-Witten theory. Another one is unramified Gromb-Witten theory. And in between, you have this epsilon unramified Gromb-Witten theory. And so Gromb-Witten theory is characterized by these contracted components over here. So you have this contracted components mapping to some points in your target. Unramified Gromb-Witten theory is characterized by this existence of these bubbles. And then you have epsilon ramified theory, which is a mixture of both. You have both bubbles and contracted components, but up to some weight, up to some degree. And now, as you change epsilon, you go from one extremum situation to another extremum situation. So from unramified Gromb-Witten theory to Gromb-Witten theory. And on the way, you pass through walls and chambers. Inside chambers, you have the same space of epsilon ramified spaces, maps. And then as you pass the wall, it suddenly changes. And so what's so useful about this construction is that instead of now comparing Gromb-Witten theory to unramified Gromb-Witten theory, you actually can compare theories that are just in adjacent chambers. And in a fancy language, when we have, so epsilon is a stability parameter, a stability condition. When we have a stability condition, the variation of a stability condition leads to ball crossing formulas. And we kind of ball cross at each wall, and then we put it all together to compare unramified Gromb-Witten theory to usual Gromb-Witten theory. So we can prove a ball crossing formula using this epsilon ramified maps. I mean, the ideas of Chakhan, Fontaine, Kim, and Zhao from the Poisson maps actually are extremely crucial in the proof of the wall crossing formula. So let me say firstly what this wall crossing formula means in plain English. So the wall crossing formulas will compare Gromb-Witten theory to unramified Gromb-Witten theory, and the difference between the two will be measured by Hodge integrals. So Hodge integrals are integrals on a space of stable maps, so stable curves. So Hodge integrals are integrals on a moderate space of stable curves, not maps. And you integrate psi classes and lambda classes. Psi classes are classes associated to line bundles given by cotangent spaces at points, at marked points. While lambda classes are Chern classes of a Hodge bundle. So Hodge bundle is just given by differential forms on curves. So the difference between Gromb-Witten theory and unramified Gromb-Witten theory is just Hodge integrals. And though Hodge integrals naturally rise via localizations on projective spaces, for example, and essentially for the same reason they rise also in our considerations. But more specifically, in our case, the Hodge integrals are in some sense invariants associated to parameter spaces of ramifications. And what's more, this wall crossing formula, it's universal. So this Hodge integrals contribution is universal and it depends very little on x. So in some sense, for every x, Gromb-Witten theory and unramified Gromb-Witten theory are equal up to terms that depend very little on the target. Only via some simple topological data. So that's what this wall crossing formulas. Should say there is no epsilon here. So as I said, epsilon is more like an auxiliary tool that we use in order to compare theories in adjacent chambers, and then we put all together to arrive at the wall crossing formula that compares extremal values of epsilon. I'm not using quasi-maps at all here. I'm saying that the ideas from quasi-maps were useful. Sorry. Yeah, when you vary epsilon, wall crossing terms are exactly Hodge integrals. It comes. I'm simplifying the matter a bit. I'll show how Hodge integral looks like. So that's what it says in plain English. In mathematical terms, the wall crossing formula takes the following form. So it actually is true in all dimensions. It's also true for any kind of invariance. So you can also put descendant invariance, or actually you can put something else there. So, and the wall crossing formula says the following. So if we take descendant Gromb-Witten, psi classes are just classes associated to cotangent spaces at the marked points. So if we take a descendant Gromb-Witten invariance, we take then descendant unramified Gromb-Witten invariance. The difference between the two is the following formula. So what does this formula say? So firstly, there is summation over here. We sum over ordered partitions of G and the number of markings. Then for every part of this ordered partition, we have a Hodge integral. Well, this Hodge integral is, in fact, it's a class in a cohomology or projectivization of a tangent bundle with a formal variable z attached to it. It's given by Hodge integrals. On the next slide, I will actually show how it looks like. And then we substitute the variable z with a relative psi class. So there is a variable z over here. So it's kind of a rational function. And then when we plug it into this, when we treat it as an insertion over here, we substitute z with a relative psi class. And as you can see, there is a bar here. So invariants on the left are usual absolute invariants. They're associated to markings on a source. But the invariants on the right are what I call relative invariants. So they're associated to markings on the target. There is a subtle distinction between markings on the source and the markings on the target. And we have, for this wall crossing formula, we have to introduce the markings on the target in some sense. And so we treat these I functions, and then they're given by Hodge integrals, and then we treat them as insertions. So you don't need to understand this formula. I just want to show that it's a concrete formula that you can work with this formula. So it's very, you can use this formula to prove things. So let's apply this wall crossing formula in dimension 3. So as you said, there is a tangent bundle. So the actual Hodge integral looks like that. So you take so this integral takes place on mg1 times projectivization of tangent bundle. So you take Hodge bundle times z. You view z as a trivial line bundle of weight 1, of C star weight 1. You take tensor with a tangent bundle of x, and then here you have z minus h minus psi 1. H is a, well, as I said, relative hyperplane class in the projectivization of a tangent bundle. Z is just a formal variable, equivariant formal variable. And then after summing over genus, so you have these Hodge integrals, we sum over this genus, and we get the formula that looks like this. So this is exactly the same sign function to the power to the following exponent. So the way to make sense. So this is a class in a cohomology of projectivization of a tangent bundle, and to make sense of this expression, you just take log of this expression and then take an exponent of this expression. And now we plug it in. So if you recall, this is exactly the same sign functions that appeared in the comparison. I mean, the formula that compares Gopakov invariance and Grom-Witt invariance. So if we plug it into the wall crossing formula, and then I'm dropping lots of details. Essentially, it results in this formula stated in the beginning of the talk that compares Gopakov invariance to Grom-Witt invariance. In particular, so we show that unramified Grom-Witt invariance are also related to Grom-Witt invariance via the same formula. So it means that unramified Grom-Witt invariance are actually equal to Gopakov invariance in the case when there are, in the case when the target is a Fano threefold or a Clavial threefold, and the class beta is not a multiple of any other classes. And this exponent over here, it you kind of arises due to dilaton and divisor equations. So you have that exponent over there, and that exponent turns into this exponent by dilaton and certain versions of dilaton and divisor equations on an unramified Grom-Witten side. Okay, so that's all about the Gopakov invariance. Let me zoom out and talk about these wall crossings more generally. There is also idea of a proof. Yeah. So there is a. Yeah, let me first briefly mention how we prove that. So here we use epsilon. For each wall, essentially, we construct a master space. So a master space will contain spaces of epsilon ramified maps in adjacent chambers of the wall, and essentially it looks like, almost like a projective bundle. So there is a C star action, and if in a nice situation, the C star action will kind of move one space to another, and the resulting invariance will be equal. But as the C star action moves one space to another, there are some other components that are picked up on the way. And these extra components will be exactly the wall crossing components that appear in the wall crossing formula. So that's a rough explanation of what happens. So we use the master space technique to prove the wall crossing formulas. Okay. Now let me talk about these wall crossings in general. So in fact, in dimension 1 is already something interesting. So first in dimension 1, unramified Grom-Witten theory is just a Hurwitz theory, as I mentioned. So Hurwitz theory is in something much more concrete. It literally counts on the nose how many covers a curve has with a specified ramifications. It's expressible purely in terms of like topological data, the fundamental group of the curve, or also the representation theory of symmetric groups. And so for ramifications are just partitions of degree. So for each ramification profile, for a collection of ramification profiles, we can define a Hurwitz number. So this is just, it counts how many covers of degree D with a specified ramification profile a curve X has. So in this case, X now is of dimension 1. And so there is a Grom-Witten Hurwitz correspondence of Oknenkov-Pandare-Panda. What it says is that if we take descendant point insertions, or it's called stationary Grom-Witten invariance of a curve, then it's equal to Hurwitz numbers via the following formula. So there are these completed cycles. So it's just a formal expression of ramification profiles, and you plug it into this function X that spits out the number of covers with a specified ramification. So these completed cycles have a completely representation theoretic meaning. And well, in fact, this wall crossing formula also recovers this Grom-Witten-Hurwitz correspondence. And well, it recovers it in a slightly different form, so it actually expresses these completed cycles in terms of Hodge integrals. It's probably not the best expression for these completed cycles. I mean, one of the difficult parts of Openkov-Pandare-Panda work was to compute these completed cycles. And for computational purposes, expression in terms of Hodge integrals is probably not the best one, but the wall crossing gives some kind of geometric framework for this correspondence. And it also holds beyond the descendant point insertions. Okay, and so the bigger picture is the following. So let me even go beyond the unramified Grom-Witten theory. So this wall crossing is in fact not an isolated phenomenon. So there are many wall crossings of the similar kind in very different contexts. And as I said, I mentioned already before, Chakhan, Fontanin, Kim were the first ones to conjecture this kind of wall crossings in the JIT quasi-map theory. And Zhou proved their conjectures in full generality. And in fact, I mean, their ideas are extremely crucial for everything that I said. And in case of JIT quasi-maps of a quintic, for example, so Chakhan, Kim, and Fontanin proved that their wall crossing coincides with the mirror transformation of A and B model partition functions. So what it says is that if you take quasi-maps and Grom-Witten invariants of a quintic and a quasi-map invariants of a quintic, then they're related by the same transformation as a Grom-Witten invariants of a quintic and the periods of its dual. So in particular, quasi-maps over quintic are equal to the periods of its dual on a nose. So that's what wall crossing does in the case of JIT quasi-maps, and in particular in case of a quintic. So there is also another kind of a quasi-map theory called modular space of sheaves, quasi-maps to modular space of sheaves. And there is exactly the same kind of wall crossing there. And in this case, the wall crossing actually relates Donaldson-Thomas theory of a product threefolds. So S is a complex surface. Product threefold is S times C. So this wall crossing, the same kind of wall crossing relates Donaldson-Thomas theory of this product threefold with a Grom-Witten theory of a modular space of sheaves on S. For example, like a Hilbert scheme of endpoints on S, such that the domain curve and then is fixed to BC. So in that case, it's exactly the same kind of wall crossing. So semantically and symbolically, it has the same form. It just differs semantically. And so there is also another kind of a wall crossing similar to the one for the quasi-maps to modular space of sheaves. And this wall crossing relates actually Grom-Witten theory of this threefold, but now with also Grom-Witten theory of orbifold symmetric product. So in this case, it was Donaldson-Thomas theory of a threefold with a Grom-Witten theory of the Hilbert scheme of, for example, of D points. In this case, it's Grom-Witten theory of a threefold with an orbifold symmetric product. And this was actually inspiration. This result was also inspiration for the unramified wall crossing in this talk. So last slide. So what unifies this wall crossing? So essentially, this wall crossings, we trade degeneracies of our space with degeneracies of our objects. So in case of a threefold, in case of unramified Grom-Witten theory, so we traded contracted components with bubbles on the target. And in fact, this picture applies to many different situations. So you can, in quasi-map theory, you trade degeneracies of your source with the degeneracies of your maps. In unramified Grom-Witten theory, you trade degeneracies of the map, like of the contracted components, with degeneracies of the target. And for example, you can also imagine that instead of a curve, instead of a map from a curve, you can have a sheaf here. So this kind of wall crossings also apply beyond the Grom-Witten theory. So yeah, that's it. Thank you.
Thank you, Dennis, for a wonderful talk. So is there any question?
Can you use the same ideology for gauge theory? So instead of compactifying the modular space of holomorphic bundles, let's say on the surface by sheaves, replace them by bundles on these bubbled up spaces.
Yeah, you can do something like that. I don't know if it's useful or not, though. You can trade degeneracies of a sheaf with the degeneracies of ambient space over which you take the sheaves. So as you say, I think you probably can. I don't know if you can actually clean up to the point where you have vector bundles, but you have probably sheaves with a kind of fewer degeneracies. Yeah, I don't know. I mean, probably can do vector bundles. I'm not sure. Yes.
Thank you for a very nice talk. I have a question. So the degree zero maps or the trivial class map is a special case of what you're talking about, I assume. So therefore, in that context, your object in the Gromov-Witten side is the marginalized piece of Riemann surfaces with some characteristic class you have to compute. I think it's a third class of the Hodge, G minus first Chern class of the Hodge bundle. Yeah. So your method gives you a way of computing these integrals indirectly, correct?
I think in this case it gives something tautological. It gives something tautological. It will the wall crossing invariants are actually this kind of a Hodge integral. So I think it will give you something like Hodge integral is equal to Hodge integral.
But how did you know what the Hodge? I mean, the answers, for example, the McMahon, which is part of this cinch and all that you're talking. It's the sign formula knows about the answer, not the equality. Are you deriving this or using it? I'm a bit confused. In other words, if you didn't know, if you just knew the formula that we had with Gawa-Kumar, you could derive these integrals explicitly, the numbers, rational numbers. So I'm asking whether your method also gives you another way to compute these numbers.
So you have to know, let me go back. So you have to know how to compute this Hodge integral. That's all you have to know. This Hodge integral is a Hodge integral with one equivariant parameter. So it's a bit less, it's less complicated than the Hodge integrals that you obtain via degree zero from the degree zero maps. But you have to know how to compute this Hodge integral. This is input data. So
you put that in?
Yeah, that's input data. But this one is not complicated. So this is just, this is not, it doesn't have the same complexity as the degree zero.
But you can derive using that, the one I'm talking about?
Probably even simpler techniques. Yeah, I mean, you can derive it. You can derive it.
I see. I'm just wondering whether, I mean, from the physics side, that was surprising that we could compute these integrals using the physics picture. I'm just wondering whether, first of all, in your context, that would be a surprise in some sense, and if so, are there other characteristic classes you can have closed formula? So typically, one usually gets recursion relations or these things for computing these classes. In these cases, you get the closed form for all of them. I'm just wondering whether the analogous things exist for other combination of characteristic classes.
What do you mean? Yeah, I don't fully understand. So what do you mean other characteristic classes? If you put something else?
For example, the intersection of Mumford classes and so forth. If you want to compute, you get these recursion relations. The closed formula for the general formula is just obtained through the recursion method. It's not a closed formula for a given answer. You have to compute it using recursion. Whereas in these cases, you have closed formula for the answer without any recursion type thing. Are there analogous things you can compute here?
Yeah, I'm not sure. I mean, this Hodge integral, I was very lucky with this Hodge integral. The fact that I could compute it is a luck. My academic brother told me how to compute this Hodge integral, and he was probably the only person who actually knew how to compute it. It's not a difficult one though, but it's hidden somewhere in the mathematical literature. But yes, I don't know if you can use it as a
Bernoulli numbers that are there in some sense. Yes, exactly. Okay, thanks. Yeah.
Gene is zero. What?
Yeah, but that is just.
I don't know. Yeah, probably can explain. You can explain to me later.
Okay, thanks for the talk, Dennis. I had a question. I mean, in the original philosophy of Gawa-Kumar and Waffa, these were, so to say, indices of actually a cohomology theory with individual numbers. So for these primitive classes, can you say something? I mean, in some cases we can refine it in the local cases. And for these primitive classes, can you say from your perspective something about the individual positive numbers of states?
Can I say, like, what kind, like, can I derive the
I
properties?
mean, instead of
Can I-
relating to the index, can you sort of...
Can I derive, like, whether they're vanished for high enough genus or whether they're integers?
No. I meant this is an index. It's so to say a combination of a positive and negative combination of states. Can you sort of say something about the individual states from
No, I don't
for
know.
these primitive classes?
I don't think so. I don't know. It's kind of it's purely an enumerative thing. So it's just
Yeah, the other is also purely enumerative.
yeah.
Yeah, or even for the compact, if you pick a orientation, you could.
Yeah, like, we can talk. I mean, I don't fully understand the question, unfortunately. Sorry. You mean whether you can refine them or you can whether you can refine them with equivariance probably. You can in an equivariance setting, if the target has some equivariance, like it's a local surface, you can probably refine it with a. Yeah. Yeah. Yeah, I think I understand. So you mean in the case of cohomological, like Molek-Toda situation, you can refine the invariance by taking this perverse filtration, right? And then, I don't know. Yeah, I don't think you can do it here.
All right, so we'll have the last question.
So for the between quasi-maps and stable maps for the quintic, you get the wall crossing gives you like the relation between the I and j functions. Do you know what happens when you wall cross the j function over to this unramified theory?
I mean, you can wall cross it, but I don't know what you get. I don't know. I mean, yeah, j function is just some Gromit invariance, right?
Like
with descendant, the insertions.
there's no problem doing it. I'm just curious if it,
I don't
you
know
get
what,
something interesting.
Yeah, I don't know what you get on the other side.
All right, thank you. Thank you, Dennis. All right, so 3 minutes break.
Yes, because I need to find the file. Hi. The PowerPoint that you sent? Okay. A slideshow. Okay, just actually, if you resolve this better, otherwise just put it here.
How's that?
Right. Yes. Okay. It's already
Is this on? Is this hot?
Yes.
Okay. Okay, and the pointer?
So forward, backward, and if you keep pressed, you have the pointer.
Okay, so which? This is forward? Let me just play with it. chalk in case I need to answer a question. Okay.
Here.
All right. Good.
Yeah, for the pointer, you can point everywhere you want. It doesn't matter.
All right. So second talk
Barometer.
this morning will be,
Oh,
Doesn't matter where you point.
all right, second talk will be by Greg Moore from Rutgers. He will talk about update on SUSY field theory and the invariance of smooth four manifolds.
Well, there's been progress. Things are moving in the subject of supersymmetric field theory and invariance of four manifolds. I think they're moving forward. And so I'd like to tell you a little bit about that today. And thank you to the organizers for the opportunity to do so. So let's begin with some motivation. Let's recall the glorious history of the relationship between four-dimensional field theory and four-manifold topology. In some sense, it began with the discovery of instantons in 1975, which led rather directly to the discovery of Donaldson invariance, which also led rather directly to topological quantum field theory. And that was at least part of the motivation for the renowned work of Seiberg and Witten, which led to a revolution both in string theory and in differential topology of four manifolds in 1995. Now, it's obvious to you that not all questions in string theory are answered. Maybe less obvious is that not all questions in four-manifold differential topology have been answered. One way to make that point is the following. Let's let X be a four-dimensional, smooth, compact-oriented manifold without boundary. For simplicity, we'll take it to be connected and simply connected. And an essential assumption in Donaldson and Seiberg-Witten theory, they're really the same, is that X admits an almost complex structure. Well, under these conditions, that means that B2 plus of X is odd. There's no reason in the world for a four manifold to have B2 plus odd. For example, the four sphere has B2 equals 0. So in some sense, we're missing half the world of four manifolds. Now, we'll relax that condition at the end of the talk, and whether that's significant or not, I do not know. But it just is one of many indications that there's a lot left to learn. So as a physicist, that motivates me to look at various generalizations of the Donaldson-Witten paradigm. We could look at other four-dimensional theories. We could look at five-dimensional theories, six-dimensional theories. We could couple to background supergravity. And these might lead to truly new invariants that are independent of the Donaldson and Seiberg-Witten invariants, or they might not. By truly independent, I mean distinguish two homeomorphic but not diffeomorphic four manifolds, which can't be distinguished by Seiberg-Witten invariants. That's a tall order, and it would be unwise to use that as a measure of success. So in today's talk, I'll show you that some of these generalizations lead to interesting issues in quantum field theory, analytic number theory, and topology. So I think it's still worth thinking about. All right, so now I begin by talking a little bit about topologically twisted four-dimensional n equals 2 theories. As I'll explain a little more, it's based on just a group homomorphism. So in that language, Witten's original example is based on a homomorphism of SO4 to be thought of as the structure group of the tangent bundle of a four manifold into spin 4 times SU2, SU2 for R symmetry, divided by the Z2 subgroup, which is a distinguished Z2 subgroup. It's the one that acts trivially on the vector multiplet representations. It's a small calculation. And then when you make the twisted Super-Yang-Mills theory based on this homomorphism, you get a function on the homology of the four manifold, which only depends on the oriented diffeomorphism type and a choice of a Tufts flux. But for other four-dimensional n equals 2 theories, one must choose other tangential structures, tangential structures in the sense that Arun used at the beginning of this week. You must choose other tangential structures to define the twisted theory. So for example, for n equals 2 star, one must choose a spin C structure. And then the twisted partition function, it's a function on the homology of your form manifold, only depends on the oriented diffeomorphism type of X, a choice of a tuft flux, and a spin C structure, an ultraviolet spin C structure. So it's a natural question. What is the general tangential structure that you need for twisted four-dimensional n equals 2 theories? And work in progress with Vivek Saxena, who's a postdoc at Rutgers and needs a job, and Ranveer Singh, who's a graduate student at Rutgers. We're investigating that question. So the natural first thing to do is to look at Lagrangian four-dimensional n equals 2 theories, and there we have an answer. I'll show you. And our goal is to answer it further for general arbitrary class S and maybe general four-dimensional n equals 2 theories. So first with the Lagrangian case. What's the basic data you need to define a renormalizable Lagrangian d equals 4 n equals 2 theory? Well, we're going to have a gauge group, and that gauge group is going to have a simply connected cover. So that'll be G tilde, some semi-simple compact Lie group. And then we're going to choose a quaternionic representation of G tilde. And with a suitable metric, the commutant of the gauge operators gives you the flavor symmetry group. And so now we form this group, product of 4 factors, G tilde, spin 4, SU2R symmetry, and the flavor group. So we've got this group. And now to define a physical theory, we need to make a choice of a finite abelian group, C physical, in the center of G tilde cover. And it should act trivially on our hypermultiplet representations. And then the fields of the physical theory are based on a bundle, P physical with connection, for a structure group, which is this quotient. So then we can say, what is the set of all fields? Or in the sense of Fried and Hopkins, we should actually speak of a sheaf of all fields, a sheaf on man. Well, we have the bundle with connection. We'll have a flat gerb. If you like this terminology, it's a one-form background gauge field for the one-form symmetries. And you'll have masses, couplings, and hypermultiplet fields. I'm going to be focusing on number 1 here. And it's very useful to use a very simple mathematical idea here called transfer of structure group. If I have a homomorphism of groups, G1 to G2, then I can map a principal G1 bundle, P1 over M, to a principal G2 bundle, phi, I'll call it phi lower star of P1. And one way to think of it is if you like transition functions in patches, and you have transition functions into G1, you just apply the homomorphism to it, get transition functions into G2. Phi is a homomorphism, so the co-cycle condition is still true. A more sophisticated way to say it is that you can do the associated bundle construction, or if you like, if you have such a phi, then you have B phi from BG1 to BG2. Anyway, you look at it, you have this transfer of structure group. And this phi star extends to the category of bundles with connection. If you have a connection nabla 1 on P1, you get a connection nabla 2, which I'll call phi star nabla 1 on phi star P1. And all you got to do is compute the holonomies of the connection nabla 1, apply the homomorphism to it, and get the holonomies on for nabla 2. You declare those to be the holonomies of nabla 2, and that defines the connection nabla 2. Okay, so now we have this covering group, and so we have 4 group homomorphisms, which are projections to the 4 factors. And using this terminology, what is P1 star? Well, those are our dynamical gauge fields. What is P2 star? Well, that's going to be fixed to be the frame bundle with the connection, a Levi-Cevita connection for some Riemannian metric. P3 star is going to give us the R-symmetry bundle and connection, and P4 star, the flavor bundle and connection. And when I think about these things, I usually think of these 4 pieces of data separately. But I want to encourage you to think of them all as being one part of data for P physical and novel physical, because after all, that division by the finite group C is tying them together. So that point of view is very useful. For example, it dispels a misconception that I've had for a long time, which is that sometimes it's said that you can't define these n equals 2 theories on non-spin manifolds because you have fermions in the theory. But in the twisted theory, we haven't gotten to twisted theories yet, but in the twisted theory you can because the fermions become differential forms. I think that's actually a misconception. What you need is a principal bundle with this structure group. So if the image under P2 times P3 of this finite subgroup contains this magic Z2 subgroup, which acts as 1 on vector multiplets, then these bundles can very well exist on non-spin manifolds. Has nothing to do with the twisting of the theory. So these theories, the physical theories, if you like, can exist on non-spin manifolds. What you need is a principal bundle, pointer. What you need is a physical bundle for this a well-defined bundle with structure group G physical. Now, I won't say so much about the role of the gerb. That's there to allow the introduction of a tuft flux. That's best done in the slab or sandwich or quiche or SIM-TFT picture. Sakura was talking about that yesterday. And the application of those ideas to this particular problem is in my paper with Fried and Telemann and doubtless many other places, and is well explained in more detail in Dan Fried's write-up of his String Math 2022 talk. In any case, this gerb has a characteristic class, which is in H2 with finite group coefficients, which are just the projection under P1 of this C physical that we had to choose to define the theory. I think in view of time, I'll skip over an interesting necessary condition on the one-form symmetry fields. So we've got these physical fields, and the next thing we want to do in the quantum theory is we have to decide what's dynamical and what's background. Well, the first thing to choose are what are the background fields. Typically, that'll be a subsheaf of the sheaf of all fields. So we'll have a map from the physical fields to the background fields. And in general, the dynamical fields are the fibers of pi. And in general, that fibration is non-trivial. That just means that what you define as your physical fields depends on what the background fields are. Now we have an exponentiated action on the space of all physical fields. And you should think of the partition function as a function of the background fields as some kind of push forward of phi under pi. And that'll be an important point of view at the end of the talk. So now we're ready to start talking about topological twisting. So the idea is to upgrade Witten's homomorphism to a homomorphism I'll call phi twisted from a group G twisted to G physical, and define your dynamical and background fields by saying, okay, we have a principal bundle P twisted for G twisted. We take an arbitrary connection on that, and then because we've chosen an astute homomorphism, if we make this push forward, then our partition function will be invariant under continuous deformations of the background fields for this twisted bundle. And that'll be true for the usual reasons that there exists a Q such that Q squared is 0. So here's the picture. This is the usual physical picture. Now we're going to find an astute subset of the set of all physical fields defined by this homomorphism, such that if we take the path integral, it's independent of continuous deformations of the connections, the background field connections. And so what Vivek and Ranveer and I did was we constructed an explicit group. It's just G tilde times spin 4 times TF, and an explicit finite abelian group and homomorphism such that this all holds. And then the twisted partition function will depend on the diffeomorphism type of X, the 't Hooft flux, and what I'll call a generalized spin C structure. So I'm defining it here. It's a principal bundle for this structure group, spin 4 times TF, a torus, divided by a finite abelian group, such that if I project on the first factor, I get the frame bundle of X. Now, just like symmetries, generalized symmetries, and their 't Hooft anomalies, the topological twisting data should be an RG invariant, so it should be possible to extract the fields F twisted directly from the low energy effective Seiberg-Witten theory. We haven't done that. We did it by starting with a non-abelian ultraviolet defined Lagrangian theory, but it should be possible to extract the same data from the Seiberg-Witten theory. And that would be a good thing to do because it would allow us to find the twisting data for generalized class S theories. But since I'm pretty confident that it can be done, I'll stick my neck out and make a conjecture that for any four-dimensional n equals 2 theory, Lagrangian or not, class S or not, as long as I have twisted masses, it admits a topological twisting with a twisted partition function, which is only a function of oriented diffeomorphism type. The isomorphism classes of the background gerbs for the one-form symmetries, and what I just defined as generalized spin C structure. Okay, so that's what I had to say about topological twisting. Any questions? Okay. So C is going to be such that I have a homomorphism to SO4. So it's just a principal bundle for this structure group such that, so I have projections P1 to spin 4 such that P1 star is equal to the frame bundle of X. That's a generalization of the usual definition. All right, so I want to review very briefly, since you've all seen it many, many times, the Donaldson-Witten paradigm. So we're going back to Witten's paper from 1988. He has an SU2 vector multiplet. So he has a connection on the gauge bundle in the notation of the first section, that's P1. And he has a Q symmetry, and the image of the gauge field is one-form fermion. Those are part of the twisted fermions. Q on the fermions is a gauge transformation by the complex adjoint valued scalar field, phi, which itself is Q invariant. So we'll see these equations again at the end of the talk, and an important viewpoint on those equations, pointed out by Beaulieu and Singer, I believe, is that these are the equations that define G equivariant cohomology of the moduli space of gauge connections, where curly G is the group of gauge transformations. Now, back to Witten's paper. How do you construct observables? Well, phi is Q invariant. You want to make it gauge invariant, so you take the zero observable as the trace of phi squared. Part of the twisted supersymmetries is an operator K, such that the supersymmetry algebra becomes K with Q is the exterior derivative, which means we can form J-form operators by acting with K, J times. We can integrate those J-form operators over closed J cycles, and that defines a Q-invariant operator, which only depends on the homology class of this sigma J. So Witten defines a function on the homology of the four manifold. ZW of a homology class is just taking the correlation functions, the generating function for the correlation functions of O sigma. And one of his main statements is that that is independent of the metric on the four manifold. And then it was shown that this path integral localizes to an integral over the moduli space, or people tell me it's better to say moduli stack here, the moduli stack of anti-self-dual gauge connections where F plus is, that's my definition. And okay, so we localize to that. Now, meanwhile, Donaldson had defined a map, mu, the famous mu map, from the homology of the four-manifold into the cohomology of the instanton moduli space, or stack. And so Donaldson defines his function on the homology by saying, okay, let's exponentiate mu of sigma and integrate over moduli space. And he shows that even though the moduli space depends on the metric, this function z Donaldson does not. And so another main claim of Witten's paper is that z Donaldson is z Witten, so let's call it the Donaldson-Witten function, and it only depends on these two pieces of data, the oriented diffeomorphism type and a choice of a Tufts flux. So then the question is, how do we evaluate it? Well, since it's independent of metric, we can scale up the metric, which means we can evaluate it using the low-energy Seiberg-Witten low-energy effective theory. And that turns out to be a sum of two terms. I'll call it the Coulomb branch term and the Seiberg-Witten term. And I said it was metric independent, and I lied. When B2 plus is equal to 1, there's a little bit of metric dependence. When B2 plus is 1, H2 plus is a line inside the cohomology, second cohomology of X. And so these terms actually depend on a choice of oriented line in that space, the oriented line being defined by the self-dual forms. Now, an important point from my paper with Witten in 1997 is that one can deduce the Seiberg-Witten contributions from the Coulomb branch contributions, and therefore it's logical to start with the Coulomb branch contributions. So what is the Coulomb branch contribution? Well, that's an integral over the Coulomb branch of vacua of the theory on R4. So for G equals SU2, a single vector multiplet, we have the Coulomb branch parametrized by the expectation value of trace phi squared, and then the measure is computed using the low energy effective theory for a single vector, a U1 vector multiplet. And famously, that low energy effective theory is derived from the Seiberg-Witten geometry of a family of holomorphic Riemann surfaces, elliptic curves in this case, equipped with a holomorphically varying one form which is itself is meromorphic on the surface. Okay, now what Seiberg and Witten also showed is that the effective action is very nicely written if you have a modular parameterization of the U-plane. And that modular parameterization in this case turns out to be given by a Haupt module for gamma upper naught 4, this modular function for gamma upper naught 4. So here's an example of a fundamental domain for gamma naught 4. So now the Coulomb branch integral is going to be an integral over that fundamental domain of a function h of tau, which is holomorphic and metric independent. And it turns out a total derivative with respect to tau bar of some function g hat. So this g hat comes from the photon path integral. It's not holomorphic in tau. And disturbingly, it's continuously metric dependent. But nevertheless, when you do the integral over the tau fundamental domain, it turns out that it only depends on the metric through this j. Now, this g of tau is a Mach-Jacobi form, and the theory of Mach-Jacobi forms is very useful in dealing with these integrals. That's where the analytic number theory comes in. Anyway, once we have the integral in this form, since g hat is suitably modular, we can just do the integral by parts, and the boundaries of the fundamental domain cancel out except around the cusps, and so you get a sum over the three cusps of the constant term and a Q expansion of some modular object. The three cusps are the weak coupling domain and the monopole and dion points at tau equals 0, 0, and 2, which correspond to u equals plus and minus lambda squared. And so the integrals around those cusps spoils topological invariance, so we add back in the Zyberg-Witten contributions. That's the sum over infrared spin C structures. Has nothing to do with the ultraviolet spin C structures that you need for theories of matter. The infrared spin C structures of the Zyberg-Witten invariant and a trigonometric function of the homology class, which you compute from Z Coulomb. Now, what do the other Lagrangian theories compute? Well, the path integral for those localizes to an intersection theory on another moduli stack, which is the moduli stack of non-abelian Zyberg-Witten equations, as was pointed out by these gentlemen a long time ago. So instanton moduli space is a very special case. What are the non-abelian Zyberg-Witten equations? Well, referring back to the discussion of general twisting, we have this group, which I called G twisted, and we had the constraint. Well, we put an extra constraint. We have a constraint that it's a generalized spin C structure with a generalized spin C connection. And then we take our hypermultiplet representation. Let's, for simplicity, say it's V plus V star. V is a complex representation of G tilde, such that V tensor S plus is a representation of G twisted. Then there's an associated bundle, V, to the principal bundle, P twisted, and then we can write these famous non-abelian monopole equations. So we're going to be doing intersection theory on that moduli space, but to do that, you need an orientation, and for some reason, nobody seems to have asked themselves how you oriented the space. So in discussions with Dan Fried and Mike Hopkins, we're seeking to describe the five-dimensional invertible theory whose Hilbert space on a four-manifold is the orientation line of M. And, well, so far, the concrete results are just for instanton moduli space. In that case, my role has been as chief cheerleader and pest, a little bit like the role of Edmund Halley in the invention of the publication of the Principia. So, so Fried and Hopkins construct a KO class on the moduli stack of all connections that restricts to the tangent bundle on the instanton moduli stack. That's not hard. I can do that myself. But they also use some rather elaborate topological methods to compute the first and second Stiefel-Whitney classes of this KO class. And rather astonishingly, it turns out to be cohomological in terms of Wi of x and Wi of p, which is a big surprise since we're basically calculating mod 2 indices in KO theory. Meanwhile, I was also a pest with Edward Witten, and we did a little calculation. I'll tell you some more about it later. And the Fried-Hopkins result is consistent with the mod 2 index calculation that we worked out in January. So I'll come back to this point pretty soon, because now I want to talk about the K-theoretic Donaldson invariance. Do it for time, okay. So this is an idea that goes back to work of Nekrasov and Losev, Nekrasov and Shadashvili in the late 90s. With these people, I've been studying this topic since September 30th, 2021. So for a little while. That's Jan Manscott, Xinyu Zhang, who is probably in the audience, Runkai Tao, and Hyun Kim. So the idea is to start with n equals 1 five-dimensional super Yang-Mills. So what's our structure group? Our structure group, well, for simplicity, we're going to take gauge group SU2. The other factors you're familiar with, maybe not the U1 factor. So we have a theory of a vector multiplet. So we have a gauge field. And so we have a current in 5 dimensions, which is just the trace of F wedge F. That's closed. And pointed out by Zyberg long ago. And therefore, since we introduce all background fields, we should introduce a background vector multiplet for this instanton symmetry U1, for this instanton U1 symmetry. That's what I'll call it. So the AI will be a connection on a principal bundle, PI, for this principal U1 bundle over X5, whose structure group should be thought of as this U1 instanton symmetry. Now, we have a gauge field. So we have a gauge field, AI, and we have an electric current, so it makes sense to look at the electric coupling of the instanton particle. Or if you prefer to think of it this way, it's a mixed Chern-Simons term. Both points of view are valid. That's an interesting term to look at. Supersymmetrization of this term turns out to give the entire 5-dimensional super Yang-Mills action coupled to the background vector multiplet VI. So you start supersymmetrizing that term, and then you get, for example, this standard term in Yang-Mills theory where sigma I is the gauge coupling. And just to show you that we're honest, just to show you that we're honest people, that's the full action. There'll be a quiz on that at the end of the talk. So now if you look at this, there's a gauge field here, so you might worry, is it globally well-defined? And at first you think yes, and a nice way to see that is to use differential cohomology. So our instanton symmetry U1 bundle PI with its connection defines an element of the second differential cohomology of our 5-dimensional space-time. Meanwhile, for the dynamical gauge field, the Chern-Simons invariant defines an element of differential H4. And so we just multiply and integrate in differential cohomology, and we get something in differential H1 of a point, which is R mod Z. And so we get an action when we put it into the exponential. But then, well, almost globally well-defined. When the Tuft flux of the gauge bundle is not 0, then the instanton particles have fractional charge, so the exponentiated electric coupling can have an anomaly. And again, part of the discussion with Fried and Hopkins is that we are expecting that to be canceled by the anomaly in the fermion determinant for the gauge enos. That's something under discussion, but Fried and Hopkins have an absolutely general formula for all possible fermion determinant anomalies, and so it's just a matter of specializing that formula. So now to get to the K-theoretic Donaldson invariance, we take X5 to be a product of X4 with a circle, and we specialize our instanton symmetry gauge connection in the following way. We say that its holonomy around the circle is independent of X4. We say that Pi and Fi are pulled back from X4, and under those circumstances, we can define a partial topological twist, again, based on transfer of structure group. And the background, here I was lazy. I left off the first and final factors. We're just focusing on these factors. And the background fields, again, are just the push forward of the Levi-Cevita connection. That's topological on X4, but a non-topological spin theory on the S1. Indeed, the Q symmetry squares to translation along the S1. So, since it's topological on X4, I can shrink the X4, and I get the twisted theory becomes a theory of a super quantum mechanics whose target space is the moduli stack of instantons, something that was already foreseen by Nikita back in 1996. But again, something that nobody seems to have worried about is that there are potential global anomalies. I just told you that the 5-dimensional determinant probably has an anomaly, is probably not well defined on A mod G, and a manifestation of that is that the fermion determinant of the super quantum mechanics with instanton moduli space as target is not going to be well defined on the loop space of the instanton moduli space. That's part of a very general statement pointed out by Witten and Atiyah in 1985 that if you have a super quantum mechanics and the target space is even dimensional but not spin, then the super quantum mechanics is anomalous. Well, so we want to know, is the moduli space spin or not? Again, this is all controlled by the same 6-dimensional mod 2 index in KO theory. And as I mentioned before, a little calculation with Edward gave a useful formula for it. So a special case of our result is that if X admits an almost complex structure and our gauge group is PSU2n, has to be even, then M is spin. if and only if the tuft flux dotted the second Stiefel-Whitney class of the tangent bundle is 0. Note, by the way, this is a little surprising. It's independent of the instanton number k. And with a little bit of work, you can sit down with Fried and Hopkins, and it turns out to be completely consistent with their more general formula. Okay, well, that means that if this is not fulfilled, then our superquantum mechanics is anomalous. But we definitely want to think about the k-theoretic invariance when this product is not 0. So what do? Well, we go to the electric coupling of the instanton particle. And in the case where x5 is x4 times s1, we reduce on x4, then we get a superquantum mechanics on the instanton moduli space. Well, the collective coordinate discussion of that term leads to a line bundle with connection, I'll call it Li, over the instanton moduli space. Again, differential cohomology is very useful for understanding why this should be true. So as I said before, the instanton symmetry bundle with connection defines an element of differential H2 of x4. And now if I take the dynamical field on x4 and look at the universal connection for it, that Chern-Simons term for that defines an element of differential H4 of x4 times the space of all connections. And if we multiply and integrate now over x4, well, 2 plus 4 minus 4 is 2. So we get differential H2 of the moduli stack of all connections. Well, differential H2 is a line bundle with connection. So we get a line bundle with connection. But something that I found with Hyun and Jan and Runkai and Shinyu quite some time ago is that this electric coupling indeed has a global anomaly sometimes when the tuft flux of the gauge bundle dotted into the first Chern class of the instanton symmetry bundle is not 0. So here's the condition, we think, for anomaly cancellation. The tuft flux, oh, that should be a P1. That's a misprint right over there. The tuft flux of the gauge bundle dotted into W2 plus Ni should be 0. And in that case, the fermion determinant times the holonomy of this connection on instanton moduli space should be well defined. In fact, I would further conjecture that what we're really doing here is constructing the quote U1 gauge field of a spin C structure on the moduli space of instantons. So yesterday in Edward's lecture, he showed how many structures on space-time transfer into analogous structures on instanton moduli space. Interestingly, that's not true for an almost complex structure. But if X4 admits an almost complex structure, then the moduli space is spin C. So that's a very weak piece of evidence for this conjecture. So when the global anomalies cancel, then we have a well-defined partition function. And what's it a function of? As usual, we have these two items. It's also a function of the first Chern class of the instanton symmetry bundle and a dimensionless version of the radius of the circle. So this curly R expressed in 5-dimensional terms has this formula, r to the 4th minus 8 pi squared, the radius of the circle over the 5-dimensional Young-Mills squared plus I theta. So the partition function as a function of R and the first Chern class then looks like this. It's a power series in curly R. The powers are the dimensions of the instanton moduli space for various components labeled by instanton number k. And the coefficients are the Witten indices for the superquantum mechanics with that component of instanton moduli space, which in good cases will be the L2 index of this Dirac operator coupled to this spin C connection. So because we've got an index and not just intersection theory, that's, I think, why Nekrasov, Losev, and Shadashvili called these the K-theoretic Donaldson invariants. Okay, so these were studied by mathematicians, Gutta, Nakajima, and Yoshioka, and what we add is we study this using both the Coulomb branch integral and for a toric-Kähler manifold toric localization. So the story looks very similar to what we found in 4 dimensions, and because time is running short, I'm going to go very fast through this. So you have a Coulomb branch plus a Seiberg-Witten term. The Coulomb branch is based on the Coulomb branch integral. What's the Coulomb branch? Well, again, for SU2 gauge theory or SO3, it's parametrized now by the supersymmetric Wilson line. And importantly, there's a one-form symmetry that flips the sign of the supersymmetric Wilson line. And now the Coulomb branch turns out to be a branch double cover of the modular curve for gamma naught 4. Here's the formula for the branching. So here we have the fundamental domain for gamma naught 4, similar to what you find in SU2 with fundamental flavors. There's a branching, so there's one branch point in there. Now, if you look at the formula for the double cover, the one-form symmetry is also the deck transformation of the double cover. And now if you look at the Coulomb branch integral and compute the way the measure changes under the deck transformation, it's exactly the same phase that we saw for anomaly cancellation. And so interestingly, the Coulomb branch integral is 0 when there's a global anomaly, which leads to a lot of interesting conceptual issues, but I'll skip over that. I want to skip over the detailed form of the Coulomb branch integral. But once again, it's the integral of something holomorphic times a total derivative. It could be hard to find that total derivative. For that, you need Mach modular forms. But you can find it. And so now it looks like exactly like what we had in 4 dimensions. You just do the contour integral, and you get the constant term around the various cusps. And if you do that, you get the wrong answer. It disagrees with Gucha, Nakajima, and Yoshioka. So something funny, I think we've been confused about this for 2 years, but now I know the answer. Okay, so here's the answer. So the point is that there's a subtle order of limits here. We can take the radius of the circle to 0, or we can take the weak coupling limit. So the Haupt module blows up in the weak coupling limit. Here's the formula for the double cover. Now just look at that formula. You can do this in your own head right now. If we take curly r goes to 0, then obviously u goes to plus or minus 2. But if we take r fixed and take m tau goes to infinity, u goes to infinity. So the picture as r goes to 0 is that we have scaling regions around u equals plus or minus 2. They're related by the double cover or the one-form symmetry, which look like 4-dimensional physics. And in the modular domain, it's the region under the branch point. The position of the branch point goes like I log 1 over r. So what we should do is we should do the integration by parts, get the sum over the cusps, where we take the constant term, but in here we should first expand in r and then take the constant term in the q expansion. So if you take the q expansion at finite r, you get the wrong answer. If you expand in r and take the q expansion, you get amazing agreement with Gucha, Nakajima, and Yoshioka. Okay, so I'm pretty short on time, so let me say quickly that all of this should generalize to 6 dimensions, but it hasn't been done. So I want to go to the end section. So that's another generalization of these of the Donaldson-Witten paradigm, and those are the family Donaldson invariants. So this is an interesting generalization to families of 4 manifolds, which was mentioned by Donaldson a long time ago. A modest amount of work has been done on it in the math literature, but nothing in the physics literature until I started working with Jay Cushing, Vivek Saxena, who you've already met, who needs a job, and Martin Rocek, whom you all know. So we have families of metrics. So we're going to consider the twisted theory for a family of metrics parameterized by some s, as is in some parameter space. Now, as we already know, the Donaldson-Witten function, as a function of the metric, is independent of the parameter. But when you couple to supergravity, you get not a function, but you get a whole inhomogeneous differential form on parameter space. And it's a closed differential form. So you get something like this. And now if you integrate that over closed cycles in your in your family, you could get something interesting. Those are the family Donaldson invariants. Interestingly, as far as we can see, there's no restriction on B2 plus and no assumption of almost complex structure. Whether that's significant or not, I do not know. So once you're talking about families, you might as well talk about the universal family, the space of all metrics mod diffeomorphisms. And that's a topologically interesting space because, after all, the diffeomorphism group has interesting topology. For example, the four-dimensional mapping class group can very well be non-trivial, and that corresponds to pi 1 of met mod diff. Now, I remind you of what Ballieu and Singer taught us about Donaldson-Witten theory. If we have a principal gauge bundle over X, then we can look at the G equivariant cohomology of the space of all connections, where curly G is the group of all gauge transformations. And then these equations, which I flashed before, are just the equations for the Cartan model differential of equivariant cohomology. And so from this point of view, Z Donaldson-Witten is just the push forward in G equivariant cohomology. Now, let's introduce the group of oriented diffeomorphisms of X, and we can write again the G equivariant cohomology of the space of metrics. And in physics notation, it looks like this. So it's very simple. And a very interesting and non-trivial thing is that these equations, exactly these equations, arise from a truncated and twisted n equals 2 superconformal gravity. That a lot of work went into that statement. The phi upper mu is a ghost field. Then the action, the exponentiated action, is a closed equivariant class in the G semi-direct GD equivariant cohomology of metrics times gauge connections. So we push forward in G equivariant cohomology, and at least formally, we should get a GD equivariant class on the space of metrics. And heroic calculations by Jay and Vivek derive explicit actions by coupling to truncated and twisted n equals 2 conformal supergravity. So the end result, after a lot of processing, is very simple. Let's just focus on the first term in the gravitino. It couples to the lambda mu nu, whose Q gives us the energy momentum tensor. And there are a lot of formulas for the other terms. So the very simplest example, what's the very simplest example of a family Donaldson invariant? Well, you take an element of the four-dimensional mapping class group. It corresponds to a non-trivial cycle in met mod diff. And so we integrate over that cycle, and so that translates into this expression here. We should just integrate this. But this expression is very funny, because Q on lambda mu nu is the energy momentum tensor. So lambda mu nu is not Q closed, so it's not at all clear that our period integral localizes to the moduli space of instantons. So that's both a bug and a feature. It's a challenge and an opportunity. It's an opportunity because maybe we'll see something that we don't see about topology of four manifolds just from instanton moduli space, but from this wider point of view. But it's also a big challenge because how in the world are you going to go about evaluating this thing? Well, the only idea I have about that is that an important aspect of the derivation that Witten and I gave of the Donaldson-Witten partition function used a theorem about tree-level exactness of the low-energy effective theory. And an open question is whether that persists in this family case. So how am I doing for time? Out of time, probably? Oh, really? Amazing. Okay. Okay. So I probably went too fast. So questions and future directions. So what I talked about the topological data for twisting the general D equals 4, N equals 2 theory. We answered that for the Lagrangian theories. We conjecture it for the general case. What's the invertible theory governing the orientation of non-abelian Seiberg-Witten moduli space? That's under study with Fried and Hopkins. Related to that are the global anomalies of five-dimensional super Yang-Mills I talked about. I didn't indicate this, but I don't have much to say about it, but there clearly should be a generalization to elliptic invariance from K-theoretic to elliptic invariance from 6D theories on a four-manifold times an elliptic curve. And there are puzzles concerning the generalization to family Donaldson invariants. And there are other puzzles and directions I haven't had time to mention. So thanks for your attention.
Thank you, Greg. All right.
Thank you very much for the great talk. So first I wanted to remind you something and then make a suggestion. So this global anomaly of five-dimensional theory, which is W2 times W2, was actually derived in a paper called Four-Dimensional Avatars.
Oh my
It's the analog of the shift k goes to k plus n of Chern-Simons theory lifted to the 4 plus
For an
1
arbitrary
dimension.
four manifold?
Yes, yes.
Okay, we gotta talk about that.
So the Dulac-Oxter number becomes first Chern class. Mod 2 is W2. And
Well, I had certainly forgotten about that. Okay.
now the non-trivial classes in BDIF, which you need to
BDIF,
probe
yeah.
probe your
Yeah.
family invariants. So one, and that was suggested in the paper called Issues.
Sorry?
The paper called Issues in topological field theory. So you can get them by taking the four manifold to be a product of a Riemann surface times another Riemann surface, and then Donaldson theory almost reduces to the Gromov-Witten theory with source being one curve and the target being module space of flat connections on another one. So promote that to topological string. So the A model on the module space of flat connections. So now take the true Gromov-Witten invariants. So those are gravitational invariants which you're looking for.
Let me see if I understand. That applies when the four manifold is a product or a bundle of surface over surface?
Yeah.
Okay. So
The cycles would be the cycles in MGN.
specializing the four manifold, you have that. That would be fascinating.
And then
to
you can
compare
maybe by
that,
some
yeah.
kind of wall crossing reduce many. So at least you produce lots of cycles that way.
Yeah, that's a great suggestion. So at least in that case, perhaps one could evaluate.
And finally, about the tree-level exactness. So for this gravitationally dressed Donaldson invariants, you actually need the epsilon 1, epsilon 2 corrections to the effective action.
You need the what?
So in the end, you mentioned that whether the effective action is exact at
Yeah.
the level. So you need gravitational corrections,
Oh, yeah.
which are given by epsilon 1, epsilon 2. So
Yeah, absolutely. It's the zeroth order term in the expansion of your function. Yeah, with
you
Shinyu
need
and
not
so
zero.
on, we've
What I'm
looked at
saying
that very carefully.
for this family invariance, you need all terms, not just zeroth order terms. So that it's analogous to given tiles J function in 2 dimensions. So it knows about descendant classes.
Oh, I hope you're wrong about that, because that's going to be hard. Yeah, I don't think we saw that. I mean, I should say that the main work in that section was starting with conformal supergravity, which is truly scary. You know, it'd take me an hour just to show you the whole Lagrangian. And then getting to this very, very simple, I mean, this was really, let's see. Yeah, where's it going? How come it's not going back? Okay. Yeah. Yeah, okay. That looks pretty simple. But getting there from conformal supergravity, that was the point of our paper. But yeah.
All right, so maybe you
My colleagues, so I heard your sufferings.
Oh, yeah.
A lot.
That's right. They were at Stony Brook, right?
Greg, when you discuss the five-dimensional case,
Yeah.
do you consider it important to start with an ultraviolet completion?
Well, we don't have a Lagrangian for that. So
What do you mean? The five-dimensional theory has an ultraviolet.
it has an ultraviolet completion, and I think that's important.
Which
and
one do you have? Which completion do you have in
The
mind?
E1 theory of Zyberg?
Doesn't it have a tensor multiplet at low energies?
No, I don't think so. I think it's just 5D super Yang-Mills. I hope I'm not wrong.
Well, the reason I suspect you're not right is that the E1 theory is conformally invariant in 5 dimensions, right?
Yes.
And the Yang-Mills theory has a gauge coupling constant, which I think is the expectation value of a scalar in a tensor multiplet. So I think the E1 theory at low energies has what you're talking about plus a tensor multiplet.
Gauge coupling is what? The gauge coupling, no, that's not right. In fact,
Well, the gauge coupling certainly violates conformal invariance, So if it comes from a conformally invariant theory, it's the expectation value of a field.
Oh,
which
yes,
I
it
think-
is. Yes, it is. I actually flashed it. But it comes from a vector multiplet.
Oh, well, sorry. In 5 dimensions, a tensor multiplet is dual to a vector multiplet.
That's true.
So you can say it that way.
Yeah, okay, there we go. That's the
You can say it
resolution.
that way,
Yeah.
but
Right.
But the multiplet in question isn't in SU2.
No, it's the U1. It's the U1. Okay, I'm trying to get back to where I flashed this. Yeah. Okay. It's the vector multiplet for the U1 instanton symmetry. God.
So it's really a U2 theory then?
Well,
Two-gauge
it's not
theory?
dynamic. I think we're talking about VI here. You see, here's the gauge coupling. It's the expectation value of the scalar in a vector multiplet for U1.
Okay, but when you claim there's an ultraviolet completion, that vector field is dynamical. You can't freeze it and also say that there's an ultraviolet completion.
That doesn't sound good. That would amount to an integral over R. I don't like that. Yeah, but Edward's saying it can't be non-dynamical. It has to be dynamical.
Well,
I'm
I'm
not
saying
sure
it's
about
not.
that.
I'm saying it's dynamical if you actually want to claim there's a UV completion. That's why I started by asking if you thought the UV completion is important for you to.
Well, I like to work with things where there's a UV completion, so I believe that I'm talking about something that makes sense in the UV. I can define. I could proceed with the Yang-Mills theory with a cutoff, I suppose, and think that it's not going to matter with the topological twist. I mean, the formulas, the generating function for the Witten indices makes sense, and the calculations also make sense of these Witten indices. So I would be pretty surprised if there's some fundamental problem here.
You can geometrically engineer this theory by taking type 2A on a local Calabi-Yau. Then the dynamical gauge field would correspond to normalizable two forms on this Calabi-Yau. And the non-dynamical one, which is responsible for the coupling, will correspond to a non-normalizable mode. So they should be frozen.
Well, yeah, I like that.
Sorry, it's
I
not
have to
M
reconcile that with what Edward's saying. Yeah.
Can you repeat that, Nikita?
So we start with M theory on local Calabi-Yau. For example, local P1 cross P1. So P1 cross P1 has two cycles, but in the Calabi-Yau geometry, the normalizable two forms. The L2 second homology is one-dimensional, and so that corresponds to a dynamical gauge field in 5 dimensions. The other H2 corresponds to non-dynamical gauge field, which is the coupling. And so that models SU2 theory flowing to infrared.
And maybe in the same vein, it's the UV completion is the SU2 zero Seiberg theory, no? That's engineered by the geometry that Nikita was just talking about. And there's actually a related question. If you're looking at the UV complete theory, the flavor symmetry changes, right, as this enhancement. So then your structure group that you should start with is actually different from, I think, the one that you're looking at.
Well, yeah. Okay. So let's see. I mean, one thing I should say is that I think it's important, as I was stressing, that we should be looking at these theories as series in R around R equals 0, which I think is related to this. And indeed, we're going to get to it. Skipped over this, but I think it's relevant to this discussion. Explicit results, blah, blah, blah. Explicit results, blah, blah, blah. So indeed, we're expanding in this r to the fourth. And D5, at infinite coupling, we get the E1 theory. And indeed, we're finding that all sorts of funny things are true at r to the fourth equals 1, which I think is related to what Sakura and Edward and Nikita are saying.
And can I add one other thing? So it's not just that the flavor symmetry changes, but the flavor symmetry is now not independent from the one-form symmetry. So actually, the UV complete theory has a two-group symmetry, which is broken on the Coulomb branch. You won't see it on the Coulomb branch.
It's going to be hard to see it from this point of view. So, and it's going to be hard to formulate those topological invariants because they're not Lagrangian. So, I mean, I do what I know how to do. I can work with the Lagrangians. So I need to think about this point. I don't have a good answer.
All right, is there any other question? Vivek?
I guess for mathematicians, it's been very helpful that the Seiberg-Witten invariants can be reformulated in terms of sigma model into symmetric power of surface. What is the analogous? Do you know what the analogous statement is for your this non-abelian Seiberg-Witten and so on?
I thought you were going to say it's been helpful to have a formulation in terms of Gromov-Witten, but no, I do not know the analog. I don't think Goethe, Nakajima, and Yoshioka know either. They were using Mochizuki and stuff like that. So no, I don't know the answer to that.
All right, no more. Okay, thank you, Greg. Okay. Okay, so we'll be back at 11:30. All right, welcome back. So next speaker will be Davide Gaiotto from Perimeter. He will talk about sure quantization of complex Chern-Simons theory.
Okay. I would like to describe a somewhat peculiar quantization method which seems to give good results for the definition of a Chern-Simons theory with complex gauge group. So I will start by just describing what I mean with quantization and why we should be able to find some nice examples of quantization using supersymmetric quantum field theory as a crutch. Then I will discuss how this can be applied to character varieties, which are the phase spaces of complex Chern-Simons theory, and then to complex Chern-Simons theory itself. And I will end up with a small example, which is a surprising duality between complex Chern-Simons theory and the SYK model, double-scale SYK model. So quantization. Quantization, well, of course, is a pretty familiar notion. It's the idea of a procedure to take a classical system and try to produce a quantum system. Typically, you have some phase space and some Poisson algebra of observables, say some classical functions on your phase space with a complex conjugation and a Poisson bracket. And your goal is to produce a family of algebras, non-commutative algebras, which deform the classical observables by the Poisson bracket and higher order terms. And there are two aspects to this process. You need both to define this algebra, but also to find representation of this algebra on a unitary representation of some Hilbert space. This is not an algorithm. It's an art, so it might or not work the way you want. Sometimes you might not be able to produce a quantization with the properties you like. Sometimes there will be ambiguities. In general, if you want to preserve some symmetries, for example, of your original system, this might pose some very severe constraints on the procedure. You might want to quantize in families, and this might be also an important constraint. Something which occurs in quantization is also the possibility of producing states with given properties. In classical physics, a state, an initial condition, is given by Lagrangian submanifold in the phase space. And once you have Lagrangian submanifold, you also have some sort of extra observables, which are functions on this Lagrangian submanifold, and form a module for the function on the phase space. And, well, you might want to build a collection of states which form a module for the quantum algebra of observables, which deforms the classical one. So you win if you can produce these structures. You lose if you can't. And now producing this algebra, this non-commutative algebra of observables is a rich problem. It might be difficult, might be easy. I'm going to be in a situation, I'm going to think about a situation where this problem has been solved already. So suppose somebody has already handed me some nice algebra of quantum observables and even a module of states that you want to build with some hermiticity condition. Then, in order to get a representation in a Hilbert space, you probably want for this module to be equipped with an inner product, with a positive definite inner product. Now, in algebraic language, you can imagine that you have this module, you take the Hermitian conjugate of this module, I denote it here as tau of m. And the condition of finding an inner product, which is Hermitian, is essentially the condition of finding a linear function on the tensor product of the module and its Hermitian conjugate over the algebra. Now, in this last slide, we put h bar. From now on, I will just drop h bar. And, well, this is an algebraic problem. The computing the tensor product of two modules. This tensor product might be empty. It might be one-dimensional. It might have some dimensionality. If it's empty, then you just cannot define an inner product. If it's one-dimensional, well, you'll have a unique choice of inner product, and it might or not be positive. So you either win or lose right away. If there is a finite dimensional or some space of possible tensor products, then you'll have a bootstrap problem in your hands. you'll have to find a specific choice of inner product which is positive definite. Some kind of semi-definite programming problem. And I mentioned bootstrap because this whole story sort of started from the superconformal bootstrap of three-dimensional Nickel-4 theories. So there is a certain problem that people encountered when trying to bootstrap the three-dimensional Nickel-4 theories, which, if you squint at it hard enough, looks like the problem of defining a quantum system given an algebra. And so, I started thinking about this as a way to produce quantum systems. For example, looking at the quantum systems which emerge in 3D Nickel-4 theories, you can recover a lot of, or study a lot of questions about classical representation theory. Now, you're surely very familiar with it. I mean, I use a perhaps slightly unfamiliar language here. Sorry, pointer, I need to get used to it. But this procedure is something you've done countless times during your career, for sure. Like when you study the harmonic oscillator, okay, you can do it by solving a Schrödinger equation. But a more entertaining way is to just write down, discover that there is a raising and lowering operator, that they have a nice Wall algebra, and that you can find a state annihilated by the lowering operator. Then you get a whole module for this Wall algebra by acting with a dagger. And this module happens to have a unique inner product, which is positive, so you win. If you made a mistake of looking for a state that was annihilated by the creation operator, well, you would lose, because you would immediately find that the norm of A0 is negative. Similarly, when you study representation theory of Lie algebras, you try to quantize your, or study spherical harmonics on a sphere. Again, you take SL2, you look for a representation where there is a lowest weight vector and build the module, look for an inner product, and so on. And this technology can be used in less familiar situations, like you can build unitary representations of SL2R, SL2C, other Lie algebras, quantum groups. There is quantum deformation, so this whole procedure that gives you can be applied to quantum groups. In general, so the algebra part is typically better understood than the positivity part. So the study of unitary representations of all of these objects is an old subject, but it's a subject which is still active. So there are definitely situations where you know very well the representations, but which one are unitary, it's a difficult question. Typical method that you can use to study this problem is to find some representation which is unitary, and then try to deform the module of the algebra. And positivity is an open condition, so typically you remain unitary for a while, and then some null vector will appear, and you will lose positivity. Sometimes, but actually sometimes you keep going and the null vector disappears. So I mean, I hear from mathematicians that it's a difficult classification problem. For example, for unitary representation of finite W algebras, that's tricky. And I think that the methods I'm going to describe in the rest of the talk can really be helpful in understanding these kind of problems better, or at least in providing some solutions to these problems. So I want to give a way to build positive modules or algebras which come equipped naturally with a positivity condition from a problem which initially doesn't seem to have anything to do with quantization. Okay. Now, let me give an example which will occur particularly often. So suppose I have an algebra, say defined over the reals for simplicity, but not very important, which has a positive twisted trace, which means that you have a linear function on the algebra which satisfies a condition like that. So a trace will be something where trace of AB equals trace of BA. I'm going to twist the condition by some automorphism rho square of the algebra. And I want to have a positivity condition, that trace of rho AA is positive. Once I do that, this I can think about the algebra as a module, as a bimodule over itself. So this algebra has a left and right action of A. And I can use this inner product to make the algebra into a Hilbert space. So I get the unitary representation of A tensor its opposite. Essentially, so I act on some element C in the Hilbert space by A from the left and from B, by B from the right. And it's easy to see that now the right action is Hermitian conjugate to the left action up to this twist by rho. So I've represented the algebra A as normal operators on the Hilbert space, and then, of course, its Hermitian conjugates as well. And this representation, this unitary representation, is a funny feature. There is a vector which is corresponding to the identity of the algebra, which satisfies the equation that the left and right action have the same answer, and generate the whole Hilbert space. I call this a spherical vector in analogy with things that happen in classical representation theory. Okay, so, well, what is this good for? What does this quantize? Well, it gives you a quantization of complex symplectic manifolds. So suppose you have a complex symplectic phase space, and you treat it as a real manifold, using the imaginary part or the real part of the symplectic form as a symplectic form. Among all possible functions on this symplectic manifold, there are holomorphic functions. And there are also antilomorphic functions. These are both observables, and the Poisson commute, because the Poisson bracket sort of takes either true holomorphic derivatives or true antilomorphic derivatives. So that means that when you quantize this phase space, you might try to get some observables which represent the quantization of holomorphic functions, presumably acting as normal operators, and then their Hermitian conjugates will give you a quantization of antilomorphic functions. So whenever you have a situation like this, where you have two copies of the algebra, one opposite to the other, you can think about it as a situation where these are holomorphic functions and these are antilomorphic functions in some complex phase space. So this algebraic problem of having an algebra with a positive trace gives me quantizations of a complex phase space with this sort of properties. The main challenge, in a sense, to start with is which twist to use to even begin. So I'm going to look for a twisted trace, but twisted by what? For example, suppose I take the Weil algebra. The Weil algebra has no trace. So if I do not put any twist, I have to stop immediately. But it does have a trace which is twisted by a reflection. And it turns out this trace is positive. And if you put this trace, positive trace, into this machinery, you end up with a complex harmonic oscillator. So that you have x and p, and then x bar and p bar acting on a true normalizable function on C. And this state here is the ground state of the harmonic oscillator, something like the Gaussian e to the minus absolute value of x squared. And in general, in the examples I study, the rho will emerge from a sort of bizarre procedure where you look at a complex symplectic manifold as if it was an hyperkähler manifold and do something called an hyperkähler rotation. This can take an holomorphic function into an antilomorphic function, and then you conjugate it back to an holomorphic function. And you say, why? I also ask myself why for quite a while. But you can find explanations based on Witten's brain and Gukov's brain quantization ideas. Okay, so why all of this? Sorry, it was a sort of lengthy introduction. Let me motivate why would I want to have these sort of structures. So I want to study Chern-Simon's theory with a complex gauge group, meaning SL2C. There is a potential language confusion. In the last few years, we have studied a lot analytically continued Chern-Simon's theory, which is defined as a contour integral in the space of complex connections, sort of trying to answer what happens if you take your standard Chern-Simons calculations and sort of try to change the level to be not integer or something like that. But here I really want to do an integral over the whole space of complex connections. And I want to use this action, which is the imaginary part of the Chern-Simons action for the holomorphic connection. The level in front can be any real number. What happens is that although the usual Chern-Simons action is quantized, if you look at the Chern-Simons action for a complex connection, the real part has a quantized coefficient, but the imaginary part is not quantized. So I'm not going to include the real part in the discussion, but only the imaginary part. And so I have this continuum level S. And I would like to define this theory as a topological field theory. So a well-defined unitary topological field theory. Of course, the gauge group is non-compact, so presumably there will be some thickness here and there. Maybe the partition function on some three manifolds will be infinite or something like that. But I want to really get something physically sensible out of it. This theory is historically has been studied for various reasons. One of the reasons is that if you look at SL2C Chern-Simons theory, and you decompose the connection into real and imaginary parts, it's essentially the same as the action for first order action for 3D gravity in a Lorentzian de Sitter setting. Not the same in the sense that some choices of complex connection don't look like a metric, but it's still at least evocative. So perhaps quantizing SL2C Chern-Simons theory can be a step towards quantizing 3D gravity. Okay. So until what time do I have? Because we started. Yes, okay. So 45 minutes, right? Yes, okay. Okay, so the phase space of Chern-Simons theory, you might remember, is the space of flat connections, because the equations of motion set the field strength to be 0. Complex Chern-Simons theory has a phase space which is a space of complex flat connections seen as real manifold. The natural observables are Wilson lines, holomorphic Wilson lines. So you take the holomorphic connection, you do a part-order exponential along some curve, take the trace in some representation. And they have a natural quantization. So from just standard Chern-Simons theory, we have learned how to quantize Wilson lines. There is something called the skein algebra, which it's a collection of rules on what to do when you act with one line and then the other. So you'll say, okay, something is equal to that. Something like this is perhaps rewritten as that plus various ways of reconnecting your representations and your curves. So they're precisely in the situation I was mentioning, where I know the algebra of observables I want. I know that I want this algebra and another copy coming from anti-holomorphic Wilson lines. And so if I could find some twist and a positive trace on the skein algebra, then I would get a Hilbert space, which is an action of holomorphic and holomorphic Wilson lines, and, well, it could be a good starting point. Now, it would not be enough to declare victory, because, first of all, I don't know if it exists, right, a priori. How do I know that there is a positive twisted trace on the skein algebra? And even if I find it, I might worry that it will give me a quantization on a specific space manifold, but then it will not behave well when I deform the space manifold, or when I try to compute the answer to a path integral on a tree manifold bordered by a state. So for three-dimensional topological field theory, I want to be able to, given a tree manifold with a certain boundary, to produce a state on the Hilbert space associated to the boundary. The state might be distributional if my theory is not very finite, but I want to be able to produce it. And it has to satisfy equations which are roughly a quantization of the conditions that if I bring a Wilson line into this tree manifold, I can deform it inside the tree manifold. So mathematically, there is a skein module attached to three manifolds for the skein algebra, and I want to realize this skein module in my Hilbert space, ultimately. So luckily, I don't have to, so it would totally be fun to take the skein algebra of some manifold, like a 4-puncture sphere, and do a bootstrap problem to see if I can find a positive trace. But luckily, I don't need to, because there is a different construction that gives me positive traces on the skein algebra. And this requires me to introduce the notion of Schur index. So the Schur index was originally introduced as a way to, as a specialization of the superconformal index. So every superconformal field theory has a Witten index of the space of states on an NS3, which has nice properties, is invariant of all sorts of deformations. And some specializations of the superconformal index, where some of the fugacities are set to special values, appear to have special properties. And the Schur index was one of the many possible fun specializations that the people considered. But a very nice feature of the Schur index is that it's actually defined for any supersymmetric quantum field theory. So conformal invariance is actually not needed. In a physical theory, it could be defined as counting quarter BPS local operators with some spin fugacity and a sign. But a slightly better way to think about it is that these are operators which survive the holomorphic topological twist of the theory. I will not be able to discuss what holomorphic topological twist means, but there is a manipulation you can do to the theory to produce a simplified theory, and the Schur index counts the local operators in this simplified theory. And this is useful because, although the theory is not conformal, the holomorphic topological twist kind of is. So you can put the holomorphic topologically twisted theory on the Hopf surface you heard about yesterday, and define the Schur index as a partition function. I will now make a strong assumption. I will assume that this configuration for the holomorphic twist can be lifted to a reflection positive supergravity background for the original physical theory. So the holomorphic twist considerations will allow me to sort of get a lot of algebraic information about the Schur index. But it does not give me any access to positivity, because the twisted theory is not unitary. So my conjecture is that the setting I'm studying can be lifted to the physical theory where positivity makes sense. I'm not sufficiently familiar with building Regis supergravity backgrounds to prove this statement. I really would be very happy if somebody could prove it for me. For now, I'll just conjecture it. And the formulae work, meaning that the localization formulae for the Schur index are manifestly positive, but at least reasonably manifestly positive. But okay, this is an important conjectural step that is really the linchpin of the whole construction. Now, the Schur index is a function of a power series in this parameter Q, but it actually counts with a lot of cousins. So if you take, say, any BPS line defect in your theory, you can count the operators that live at the end of the line. If you take multiple line defects, you could count local operators that live at the junctions between all of these lines. So you get a whole bunch of power series in Q. They really depend not much on the choice of line defect, as much on the choice of K-theory class of the line defect. Let me not go into this, but let's just say that these line defects have a natural fusion, and that they define some kind of an algebra, and that the Schur index only depends on, sort of behaves well under this multiplication in this algebra. So let me draw some pictures. So here is a situation where I'm counting local operators at the end of a line. Here I'm counting local operators at the junction of two lines. Here I took the second line and I merged it with the first one. And there is this sort of algebraic structure on the K-theory classes, which allows me to write the index in the presence of two lines as the index in the presence of one line, which is the product of the two. I can also take a line and bring it all around. There is a small framing anomaly that appears when the theory is not conformal. And so that if you start with L2 and you bring it all around, you might get an L2 prime. So there is a morphism I'll denote as rho squared, which tells you what happens when you rotate a line by 2 pi. And so you discover that the index, the Schur index in the presence of lines is a twisted trace. So the index of AB is the same as the index of rho squared BA. And then you can rotate a line only by pi and identify it with the line in the opposite direction. I call this map rho. And so I of rho AB tells you, counts the local operators which convert A into B. And if you, now all of these calculations can be restated as calculations on S3 times S1. So for example, the index of the endpoints of a line by the state operator map are counted by partition function where the line is placed along the S1 and at a point in S3. If I do the same for this, I get an S3 which now has 2 lines at antipodal points and wrapping the circle in opposite directions. And now the conjecture is that reflects that if this can be lifted to the physical theory with some supergravity background, there will be a positivity, so that IAB is a positive definite pairing on the space of lines, at least as long as the parameter Q is real. So these are the basic physical considerations which allow me to build a twisted trace out of the Schur indices. And these Schur indices are computed by very explicit localization formulae when your theory is Lagrangian. And there are also infrared formulae which allow you to reconstruct them from the BPS particles of the theory. So they're extremely computable objects. It's very easy to check, well, not very easy, but it's possible to check all of these properties for various simple examples, such as cyber-Witten theory. Now, okay, so the Schur index gives me a positive trace, twisted trace on an algebra, which is this algebra of fusion of lines. It's called the K-theoretic Coulomb branch by mathematicians, also perhaps by some physicists. So this is the space of vacua of the four-dimensional theory compactified on a circle. So the four-dimensional theory has a space of vacua called the Coulomb branch, which has some dimensionality. Perhaps I should draw something. Yes. So the 4D theory has a certain Coulomb branch. Think about the pictures you see in the cyber-Witten paper. And the 3D theory gains extra vacua by expectation values sort of line defects. So you get a torus vibration of the four-dimensional Coulomb branch. But if you try to find functions in this complex structure, you don't have much luck because there are no functions on tori. But if you rotate the complex structure, then this becomes an affine thing that locally looks like C star to twice the rank, but globally is complicated. And there are functions on this K-theoretic Coulomb branch, which are wrapped line defects. So this is the setting. And so the Schur index is as a quantization of the K-theoretic Coulomb branch, which is a complex symplectic manifold, as a real manifold with imaginary part of the symplectic form. This is the full statement. Now, this is true for any four-dimensional equal-to theory, but we can specialize to the class S theories. These are theories which are obtained by wrapping a six-dimensional superconformal field theory on a Riemann surface. These six-dimensional theories are labeled roughly by an ADE Lie algebra. And when you wrap it on a Riemann surface, you can add all sorts of codimension defects to enrich your theory. This produces a lot of the Lagrangian theories you know, and more. But crucially, the K-theoretic Coulomb branch is the space of flat connections on the Riemann surface C. And so sure quantization of the classes theory gives you a quantization of the space of flat connections and potentially a quantization of complex Chern-Simons theory. Even better, the action of the mapping class group, what happens to this quantization as you modify the underlying Riemann surface is controlled by the dualities of the four-dimensional equal Schur theory and is a known invariant of the Schur index. So the quantization is automatically invariant and covariant under the action of the mapping class group. The mapping class group will act on the algebra, and so it will act on the Hilbert space unitarily. And also, there is a general technology of wrapping the 6D theory on three-manifold, which can be used to give you states associated to three-manifold. So you really get all the ingredients that you want to define a three-dimensional topological field theory. The Hilbert space that you get is equipped with this interesting structure where there is a special state coming from the identity which is intertwined by holomorphic and anti-holomorphic observables. So you might ask, what does it mean in the language of Chern-Simons theory? Now, complex Chern-Simons theory with this specific action has a funny property. Chern-Simons theory usually does not have topological boundary conditions unless something special happens. Your typical boundary condition is the WZW boundary condition, which supports the Kral algebra. But in this theory, something special does happen. The holomorphic and anti-holomorphic levels are the same. And as a consequence, there are topological boundary conditions. So in particular, you can require the connection, you can define a boundary where you require the connection to be unitary. So you say, I have SL2C in my manifold, but I have EC2 on the boundary. This is a topological boundary. In a well-behaved topological field theory, it will define a boundary state for every space manifold. And I identify that with this state 1, which comes out of the quantization. Furthermore, the state that generates the whole Hilbert space by acting on it with Wilson lines. You can take these Wilson lines and bring them to the boundary. So now you have this topological boundary decorated by boundary lines. Now, this should totally remind you of something like Turai-Viro. Like in the Turai-Viro model, you literally construct a 3D TFT from a topological boundary. You have a fusion category of lines, of boundary lines, and you build your Hilbert space by decorating, by looking at skeins pretty much of these boundary lines. So this is a kind of Turai-Viro-like construction. I could even say 3D loop quantum gravity construction, perhaps. But the unitary structure, I believe, is novel. So this inner product built out of the Schur index, I think, is the new ingredient on top of this sort of, because the Turai-Viro model, in a sense, came from Ponzano-Regge, which was a way to try to build quantum gravity. So it's very natural to encounter something like that in complex Chern-Simons theory. But it's not quite obvious how to get an inner product when your space of possible lines is infinite dimensional. And the Schur index provides one such choice. And the construction also gives you naturally a sort of a novel form of complex quantum groups which will govern this complex Chern-Simons theory. Pretty much because there is, once there is a specific classes theory such that the K-theoretic Coulomb branch is the quantum group itself. So you can apply the theory to the quantum group, and you get representations of quantum groups, unitary representations of quantum groups. Okay. Now, I want to spend a slide to compare with previous attempts to build a complex Chern-Simons theory. So there are two main ideas. So the idea of using sort of the algebra of the skein algebra as a building block to build a quantization of complex Chern-Simons theory is, of course, not new. And actually, in the context of the 3D correspondence, meaning wrapping the 6D theory and 3D manifold, it could become very concrete. And it's it's absolutely compatible with that. So there were already sort of general ideas on how to build a partition function on three manifolds, but not quite on how to produce the Hilbert space attached to surfaces. So these two approaches complement each other, and they are compatible thanks to what are called this infrared formula I mentioned for the Schur index, which are sort of adapted to the cluster technology, which is used to define the 3D correspondence. Another thing you might want to compare with is holomorphic quantization. So this space of complex flat connection has a, so if you allow yourself to pick a complex structure on the Riemann surface, then you can polarize your space of flat connections by splitting it into holomorphic and anti-holomorphic parts. And you can think about having functions of AZ bar on which AZ acts as a differential operator. Now, the space of possible AZ bars is the space of bundles. And so you can try to build a Hilbert space as sort of wave functions on the space of bundles. More precisely, they are twisted half densities on the space of bundles. This is very nice. It has deep connections to two-dimensional conformal field theory. You can show that the choice of complex structure on the Riemann surface can be eliminated by, at least locally, with the help of the KZ equations. But it's kind of tricky to write, to make contact with three manifolds. Sorry. Where did I go? Oops. Don't look. Okay. Sorry. It's kind of tricky to make contact with three manifolds, precisely because you put the Riemann surface in a complex structure on a Riemann surface, and then evolving the Riemann surface into a complicated three manifold is difficult. But you can ask what's the relation between this and what I'm talking about. And, well, we have a conjecture that the state A I was discussing can be reproduced by the partition function of a WCW model on H3+, on the complex group divided by the real group, the compact group, decorated by the Linde lines. So this is nice 2D CFT, although I'm doing it at imaginary level, which is a little bit unconventional. But conjecturally, the partition function of this CFT, so this CFT can be coupled to bundles, so it gives you a function on the space of bundles, and conjecturally, it gives you a normalizable half density on the space of bundles. We haven't proven this normalizable, but I would point at sort of a tantalizing connection with what you're seeing in the case of Liouville strings. So if you remember one of the talks earlier in the week, there was a statement that you could integrate Liouville theory and imaginary values of the central charges on the space of complex structures, and it will be absolutely convergent. Here is something similar, but you're looking at this WCW theory, and you're integrating over the space of bundles. So I would definitely like to know if this integral is convergent and if it really agrees with this Schur index. So conjecturally, this gives you sort of an isometry that maps the Schur quantization into this Hilbert space. And then there is also the question if this is surjective. And I perhaps should mention briefly, if you take an S to 0 limit, so a very quantum limit, you can make contact with analytic Langlands. So this surjectivity hypothesis becomes the idea that there is a certain spectral decomposition of the space of additional model function, half densities on bundles. Anyway, sorry, this is a digression. Okay, so wave quantization. No, I want A to be normalizable. So 1 and all the states obtained from 1 are supposed to be normalizable.
Because a priori, if you have this non-compact WCW model, if your bundle is such that you have 0 modes, then this thing will diverge.
Absolutely, yes. So this
is to check the convergence.
Yes, it's not obvious. So I'm hoping it's convergent, but this is definitely a terrible object in terms. I mean, I hope that it will have some kind of square root-like integrable singularities at the wobbly locus in the space of bundles.
Because I think in the analytical lens, it was marginally converging. Like you had to just really
absolutely
log of something. So.
Yes, yes. So something like that. Well, maybe here it will be a bit better, but I'm not sure. I mean, S presumably will affect the powers that occur. Well, these are half densities twisted by an imaginary power of k. Yes, exactly. The absolute value squared is density, so you integrate it. Okay, so this was a story. I wanted to mention briefly some generalizations. There is something called the Schur half index, which you can compute if you have a boundary condition. This will count operators that you find where a line ends at the boundary. And it has, interesting properties too. It depends on the choice of bulk lines and boundary lines. Like I can have local operators, which is, I should really draw a picture for this. I can study local operators on a boundary which are at the end of two lines, which interpolate between two boundary lines and also a collection of bulk lines. Okay, I don't know how to draw things which are not on the boundary. Okay. And so the boundary lines form a module for the bulk lines, and this half index behaves as a tensor product of two modules. And there is, now we need to assume that the boundary condition admits a time reversal symmetry of some sort. I call it tau, which gives you an anti-automorphism of the algebra and maps the module to the left module to a right module, so that I can. And then I find myself exactly in the same situation as discussed at the very beginning. Yes, where I have a module and I have a tau and I have tensor product of tau m with m over a, and I need to find a positive definite inner product, a positive definite linear function on this tensor product. And well, conjecture. If you have this time reversal symmetry, the Schur half index gives you a positive definite inner product. And if so, then you can promote the modular boundary lines to a Hilbert space with an action of your bulk lines. What can you do with this? Well, Complex-Simon's theory can be defined on surfaces with boundaries, precisely because it has boundary conditions, topological boundary conditions. So you could study it on a disk, on a cross-cap, on a real projective space, things like that. This will give you some real, you can think about a theory, a surface with boundaries of cross-caps as a quotient of a doubled-up thing. You can write down the skein algebra on the doubled-up surface, and then impose reality condition to find the lines on your surface, on your surface with boundaries. And so the main challenge is to find a boundary condition in the classes theory, which will correspond to a surface with boundaries or cross-caps. The 3D correspondence can be used for that. There are some, it's not, it's not algorithmic yet, but I think it can be algorithmic. So if you can find such a boundary condition, you get a quantization of this Simon's theory in this setting. And as a test case, I want to discuss for a moment, if I can, a weird duality. So people have been studying for a while something called the SYK model. This is a quantum mechanical system which is built out of a bunch of Majorana fermions with some random coefficients. You build a Hamiltonian with random coefficients with some specific covariance. And it seems to be some kind of a dual to the gravity. And there is a certain double scaling limit. It gives you this thing called the double scale SYK model, which is a bit simpler. It depends on this parameter Q. Now, if you just open a paper on the double-scale SYK model and look at the formula in there, and you've seen some half indices, you will immediately see that these are half indices. So a lot of correlation functions look like half indices in cyber-Witten theory with normal boundary conditions. And so, well, it's almost immediate to say, okay, this is complex Chern-Simons theory. You need to dig a bit harder to find which surface is involved in the process. And it looks like complex Chern-Simons theory on a disk with one irregular puncture and this kind of SU2 boundary. Maybe it's an accident, okay? It's possible, it's just a coincidence. But maybe there is something more. Okay, SU2 Chern-Simons is not the same as 3D gravity, but it's really tantalizing. Okay.
Okay, thank you.
Usually when we connect S-class n equals 2, d equals 4 theories to complex Chern-Simons, the kind of simple observables in n equals 2 theory, BPS observables, they map to holomorphic functions on the modular space of light connections. Are you saying that you can find general functions as controllable in your approach to the quantization?
Well, you can quantize holomorphic functions and anti-holomorphic functions.
But what if
then you can
take
multiply
a product,
them. And
yes.
once you have them as operators, you can multiply them. They're normal operators.
But they don't preserve the same supersymmetry, right? In n equals 2, in d equals 4.
So, a good way to say it. What's going on is that, so imagine that this is sort of the equator of the S3. And here you have your line defects. But moving along the equator is kind of an hyperkähler rotation. If you go back to the holomorphic topological theory, where you had these lines, if the theory is not conformal, especially, the holomorphic topological twist, so you can take a supersymmetric line and make it a topological line in the holomorphic topological twist. But if you rotate the line, you need to adjust which supersymmetries you are preserving. So this line and the same line with a different slope is actually preserving a different choice of supercharges. So effectively, this line and this line are preserving opposite choice, an opposite choice. So the lines here, if the lines here are holomorphic functions, the lines here are anti-holomorphic functions. And then you sort of cut this picture and try to build a Hilbert space on which is both of these act. Yes, yes, absolutely.
When you said there's an infrared formula for the Schur index, you're thinking of this work you did with Cordova and Shao, is that right? In terms of the BPS?
Yes, yes.
The trace of the Kontsevich-Soibelman monodromy?
Absolutely.
So then is the positivity that you're conjecturing here related to the no exotics conjecture?
I think so.
Right, because
But,
if the vacuum,
it's not clear.
The sign, actually, didn't we have some positivity conjectures about those?
Yes, but, okay, let me say.
I'm wondering if it's related to your positivity.
So I put this condition, Q square, between 1 and 0. As far as I know, both for positive Q and negative Q, you get a good Hilbert space. And our positivity would tell you that certain things were positive when Q was positive. In the Schur index formula, the inner product between two things, would look like, in the formula, you get something like this. There is something called the spectrum generator. Then there are some things called frame BPS degeneracies. And you sort of, you can identify this as a state in an auxiliary Hilbert space associated to the abelian theory. Yes, and then to do this, you need to take the inner product. So you're going to do the inner product of f of A S, f of B S inside this Hilbert space. And our positivity conjecture was this: the coefficients inside here are positive. It's not really relevant for the inner product.
I think I didn't understand. Are you saying there's a positive trace on the skate algebra? Is that what you're saying?
Yes.
Are you giving us a formula for that positive trace?
Yes.
What's the formula?
Well, it depends on the surface.
Okay, you take your pick.
The Schur index for the classes theory associated to the surface.
Is there a formula which you can write down for a mathematician, or is it?
If we say I want to use the 4-puncture sphere or the 1-puncture torus, I can write an integral formula. It's very straightforward. Yes.
I have one more question. So you mentioned this connection to analytic Langlands.
Yes.
Before you take the limit to analytic Langlands,
yes,
does it still make sense to contemplate Hecke operators?
And unfortunately, Hecke operators are not there anymore. You can talk about Whittaker functional and Hecke modified Whittaker functional. So there are certain distributional states in the Hilbert space. You could totally try to ask questions about the inner product between the Whittaker functional, maybe and the states I'm defining. This would be Liouville theory. In the presence of some Verlinde lines. It almost feels, again, this is not 3D gravity, but if I could pretend for a moment this is 3D gravity, there would be a feeling of DSCFT. So this is really the CFT at the cosmological boundary.
A nice talk. So maybe my question is also related to what Nikita was asking. So in the context of n equal to 2 theories in 2 dimensions, the structure in which you have a topological theory and an anti-holomorphic version of it get combined in the context of the TT star geometry, the vacuum geometry, and all that. So in the context of the 4D, you could do the same thing, and people have done the TT star analog of the geometry in 4D, but the analog of that in 3D would be presumably. Is that related to what you're saying? Is your objects, which are real functions, related to the vacuum geometries of the 3D theory in some form?
So there is a 3D version of this story where you use 3D n equal 4 theories on S3. There are sort of 2 different compactifications on S3 that you can consider. And in one of them you put Higgs branch, and the other you put Coulomb branch local operators on the equator. So this gives you quantization here, I called it, of the Higgs branch or the Coulomb branch of the theory. If you use the hemisphere to a real version of the quantization, so that now you have some kind of module of boundary local operators, then what's happening on the S2 is the S2 partition function studied by Gomis and collaborators, which is not quite the TT star, but it's related in some way. So that's all I can say.
What's the Planck? What's the Planck?
The radius. The radius. Yes.
Any more questions?
Well, just 2 quick supplements to 2 questions that came. So on the one hand, concerning the question of normalizability of this integral over Bun-G, which gives, well, the Schur index or the representation of the Schur index as integral over Bun-G, we are currently developing some techniques for checking this normalizability. And second, concerning Vivek's question, yes, CFT does give a sort of deformed version of the Hecke operators away from the critical level.
Yes. Mhm. Yes. They're most natural placed. Sorry, wait, we're saying Hecke or Hitching? Sorry, I didn't. Yes.
To spin K over 4, I think.
Right, so in the Enikov 4 supermil Kapustin-Witten sort of picture, geometric Langland has to do with things concerning the boundary. And
Constructed an n equals 2 theory.
I know, sorry. But I would just not say that, right, the 't Hooft lines that you try to use at level 0 just don't exist in the general level. But if you have some non-pole boundary conditions, then you can put boundary 't Hooft lines, which is what I was discussing here.
Okay, yeah, I guess no more. Thank you. So there is an announcement by Pub. Okay, I guess we are back at 2. Great talk.
Unmute now.
Okay. Okay, sure. Yeah. I'll show you. Okay, great. Thank you.
Forward and backward.
Yeah. Or maybe just sorry, I misheard. Clicker is not working and in Francesco. Clicker is not working in the Francesco.
Thanks. Okay. If we have 1 minute, just let me give it. It will take literally 30 seconds. Just a question of charges. But just give it like 1 minute,
Right, yeah.
and we'll be fine. Yes.
Yep.
If you don't mind, we'll just put a little. So, just 1 minute. That will.
Yeah. Okay. Well.
Okay, but I don't know why it's changing slide.
No, it's okay. No.
Okay.
Yeah. I think. Yeah, it's working. Yeah.
Okay. You know what? If something does happen, I'll just leave this here.
Okay. All right.
And just might not put it in for like 30 seconds, and it will last
Right.
for hours.
Good afternoon. We are starting our last session, and the first speaker is Shota Komatsu from Geneva, and he will speak about categorical symmetries and scattering amplitudes. Please, 15
All right.
minutes.
Okay. Thank you for introduction, and then thank you for inviting me, and then thank you for organizers for organizing a great conference.
So yes, today I'm going to talk about one physics application of categorical symmetries, in particular on scattering amplitudes. So this is a work that I wrote together with Christian Coppetti in Oxford and Lucia Cordova in CERN in the beginning of this year, and I'm also going to mention work in progress. Okay, so let's start. So let's start mentioning about my affiliation. So I'm at CERN. So as you probably know, CERN is a big experimental facility at the border of Switzerland and France. And so what they do here is that they accelerate particles to very, very high energy, and they collide them or smash them and then measure the outcome. So why do they do this? So they want to do this because they want to compare the outcomes of the experiments against theoretical predictions. So what are theoretical predictions? So theoretical predictions are basically made by the computation of quantum field theory, and in particular, the relevant theoretical objects are what's called scattering amplitudes, or for short, sometimes people call it S matrix. And of course, every physicist knows that how to compute scattering amplitudes. And the typical way of computing scattering amplitudes is drawing this kind of Feynman diagrams. And then, so this allows you to compute probability of a particular given outcome. So this has been studied since 50s. And people found that the scattering amplitudes actually exhibit a very interesting property, which I'm going to tell you. That is called crossing symmetry. So what is crossing symmetry? So imagine you scatter particle A and particle B, and then look at the process in which the outcome is again particle A and particle B. And these scattering amplitudes or probability amplitude depends on the total energy of particle A and B, and also the angle of the emitted particles. And what people found through the computation was that if you compute the scattering amplitudes of this process, where A and B particle are colliding here, and then take that object and compute it as a function of energy and angle, and do appropriate analytic continuation, you can actually compute the probability amplitudes of completely different scattering process, in which A and A particle collide and B particle are emitted. So this is what's called crossing symmetry. So this might be a little bit vague, but it can be actually converted into a very concrete formula. In the case of 2-to-2 amplitudes and in simple cases, this basically boils down to this relation. This what's called S matrix, which computes the probability amplitudes, depend on two complex parameters, S and T, and S roughly measures the energy, and T roughly measures the angle. And the crossing symmetry basically tells you that this S matrix with argument S and T must be equal to this other S matrix, which describe the different process in which a T and S are swapped. So importantly, in the physical process, S is the energy, so it has to be positive, whereas T, which measures the angle, can be negative. So when you interpret this formula, you also need to do appropriate analytic continuation, because here originally the first argument was supposed to be always positive, but in order to make sense of this formula, you also need to consider this object for which the first argument can also be negative. So that's why analytic continuation is important. Okay, so why people are excited about this symmetry? So first of all, this is very useful for the computation, because you don't need to redo the computation of this process. You can just do the computation of this process, and then that automatically spits out the answer for this process. And as I already mentioned, this was first found through the computation already in around 50s. And in some cases, rigorous proof are obtained by these authors, and also more recently, people were revisiting this question of proving the crossing symmetry. Okay, so this is the crossing symmetry, and let me directly go to the punchline of my talk. So the punchline of my talk is that in the presence of certain categorical symmetries, the crossing symmetry that I just explained is actually modified. So in that case, we found an example in which this is actually not equal to this. And Instead, it obeys some kind of modified formula. So let me also explain what I mean by certain. So in my talk today, I'm going to only talk about series in 1+1 dimensions, although I make some comments on higher dimensions at the end of my talk. And also, I'm going to focus on specific series, which are called integrable series, in order to check the claim that I'm going to make. But the logic applies actually to non-integrable series as well. Okay? So let's proceed. So this is the plan of the talk. So I'm going to briefly review for you categorical symmetry in 1+1 dimensions. And then next I'm going to discuss the particular series that I'm going to talk about, which is integrable flow from tree-critical Ising model, and then discuss the S matrix. And then I will present how the crossing symmetry gets modified, and then gives a physical derivation of the modified crossing rules using basically the structure of the fusion category. Okay, so that's the plan. So let's start with the first bullet point. So as we already heard in several talks in this conference, modern understanding of symmetry is that symmetry based in quantum field theory basically corresponds to d-1 dimensional topological operators. So here I'm talking about what people normally call zero-form symmetry, the most canonical example of the symmetry. And in the particular case of 1+1 dimension, if you plug d equals 2, then you get one-dimensional topological operator, so it's a line operator. And so this line operator, because it's topological, you can deform it into arbitrary shape, and in particular, you can also move it in the time direction. So that basically corresponds to the conservation of the charges in the usual context of the symmetry. And furthermore, these topological lines can be multiplied, and in particular, in the usual group-like symmetry, they basically obey the group multiplication laws. And then this GAB should be some element of the group. However, it has been known for a long time, but maybe like physicists have only started to appreciate its power maybe only recently. There are actually generalization of the group, which are still topological operator, and then those are often recently called categorical symmetries. And in 1+1 dimensions, it's fully understood, and it's described by what's called fusion category. And these topological lines, which are generalization of the group-like symmetry, now obeys a little bit different multiplication law. So because here we have a sum, and then we have some integer coefficient, which needs to be positive, non-negative integer. And then this is, of course, known as fusion category, as I already said. And now you can ask, like, what is the simplest 1+1D system with this categorical, or sometimes people call non-invertible symmetry? And actually, there are a very, very simple model which exhibits this the fusion category symmetry, which probably Sakura, I think Sakura already talked about, which is Ising model at critical temperature, which people often call Ising CFT. So let me just very briefly review what they are. So 2D Ising model is something many people learned in statistical mechanical course in the university. So whose partition function is given by sum over spin. So, and then this beta is the inverse temperature. And we know that when the temperature is high, this 2D Ising model is in disordered phase, whereas if the temperature is low, it's in the ordered phase. And then there is a known duality transformation which maps the disordered phase and the ordered phase, which is known as Kuramas-Wanier duality. But this duality at generic temperature is a duality between different systems. However, if you tune the temperature to be the critical temperature, the Kuramas-Wanier duality becomes a symmetry because this duality maps the series at TC again to the series at TC. And however, this symmetry, Kuramas-Wanier symmetry or Kuramas-Wanier duality, has a little bit unusual feature. This can be understood by thinking of this 2D Ising model as some massive quantum field theory. If you interpret this 2D Ising model as a massive quantum field theory, in the high temperature phase, we only have one vacuum, whereas in the low temperature phase, we have two vacuum. So what this basically means is that this Kuramas-Wanier duality maps two vacua into one vacuum. So it's actually 2-to-1 map. So if I denote like a 2 vacuum here by plus and minus, then like the map goes like this. Plus is mapped to this single vacuum, and minus is also gets mapped to this single vacuum, whereas this single vacuum here gets mapped to a linear combination of plus and minus. And obviously, this is a 2-to-1 map, so it has a kernel. So this is why people often call it non-invertible symmetry. And you can also make it very precise. So here, this is a symmetry of the 2D Ising CFT, which sits at this point. And so this 2D Ising CFT has a Z2 symmetry, which is squared to 1. But in addition, there is this Kramers-Wanier symmetry defect, which is squared to 1 plus eta. So this is a canonical example of fusion category. And you can show that like this action is compatible with the action that I wrote here. So then you can ask, like, maybe we can ask the interplay between the scattering amplitudes and this non-invertible or categorical symmetry in the context of 2D Ising CFT. However, it turns out Ising CFT was a little bit too simple because if you compute the scattering amplitudes in Ising CFT, it's just always -1. It doesn't even depend on the total energy. So in order to see the non-trivial interplay between the categorical symmetry and the scattering amplitudes, we need to look for something more complicated. So the first thing you might try is to deform 2D Ising CFT. However, unfortunately, it is known that if you Kramers-Wanier symmetry always gets broken if you do some deformation of the Ising CFT. So now we need to look for some different theory. So what will be the simplest non-trivial theory preserving this Kramers-Wanier symmetry and has non-trivial S matrix? It turns out like you can actually easily find such a theory. To explain that, like I need to remind you that Ising CFT is the simplest unitary minimal model in 2D CFT, so which people often call M34. And the next simplest in this unitary minimal CFT is what's called tree-critical Ising CFT, which people often denote by M4,5. And it was pointed out in the literature that actually there is a deformation of the tree-critical Ising model which preserved this Kramers-Wanier duality, Kramers-Wanier symmetry. So in this like tree-critical model, there is a primary operator what's called phi 1,3. And if you deform the tree-critical Ising model with plus sign, this model actually flows in the low energy to Ising model. And along the flow, all the symmetry of the Ising model is preserved. So this gives you some non-trivial example in which the Kramers-Wanier duality symmetry is preserved. And alternatively, you can also deform the tree-critical Ising model with minus sign. But since the deformation parameter is the same, it also preserves the same amount of symmetry. However, slightly non-trivial, one difference from the plus sign is that if you deform it with minus sign, the IR phase, like if you go to the infrared phase, low energy limit, then it becomes basically gapped. And it's described by some non-trivial topological quantum field theory rather than conformal field theory like in this case. And this is basically the flow or theory that I'm going to talk about today. But let me also mention that you can also do a similar deformation of Ising model, and then that precisely corresponds to the deformation of the critical Ising model to the high temperature phase if you deform it with plus sign. And if you deform it with minus sign, you get a low temperature phase, which has 2 vacua. Okay, so now I mentioned that in the previous slide that this flow preserved the Kramers-Wanier symmetry, or more precisely like what's called Z2 Tambara-Yamagami category. So let me just explain for you the action of those symmetry on the vacua. So as I said, in the IR, we have 3 vacua. Let's denote them by minus, 0, and plus. And a Z2 defect basically, so this Z2 Tambara-Yamagami category has 2 important defects. One is a Z2 defect eta. And this Z2 defect eta basically exchanges this vacuum and then this vacuum. So this is the usual like a flipping action of the Z2 symmetry, whereas the N defect basically acts in the same way as I explained in the context of Ising model. So N defect like maps the vacuum in the middle to a linear combination of plus and minus, and then it also maps the vacuum plus to 0 and a vacuum minus to 0. So in some sense, like this is a superposition of the disordered and ordered vacua in Ising CFT, well, as far as the action of the symmetry is concerned. Okay. So in passing, let me also make some remark. So I explained this like a renormalization group flow of this quantum field theory, and then I pointed out that this deformation by phi 1, 3, in the extreme low energy, you have 3 vacua, and this 3 is actually minimal number of vacua allowed by the categorical symmetry. That basically means that you need to find the representation of this algebra, which are basically matrices in which all the elements are non-negative integer, and then the minimal size of the representation that realizes this algebraic structure turned out to be 3. And let me also point out that the similar patterns persist also for higher minimal models. So if you start from higher minimal models and deform it by minus phi 1, 3, you go to the next minimal models, whereas if you deform it with plus phi 1, 3, sorry, if you deform it by with minus, you get gapped vacua, gapped theory with n minus 1 vacua, whereas like if you deform it with plus sign, you get the next minimal model. Okay, I guess so far so good. So now let me focus on the theory that I want to study. So this is the theory that describes this renormalization group flow, starting from the UV tricritical Ising CFT to the IR TQFT. So this deformation actually turned out to have an extra interesting property, which is called integrability. So let's consider this tricritical Ising CFT deformed by minus phi 1, 3. At the UV fixed point, which is described purely by tricritical Ising CFT, there exist infinitely many higher spin currents. And that is simply a consequence of the Virasoro algebra, because Virasoro algebra is an infinite dimensional symmetry algebra, and many generate, you can construct many charges which have higher spin, non-trivial spin, higher than 2. And it was shown by Zamolodchikov that these higher spin charges actually survive the deformation. So you can just check that whether this deformation commutes with these higher spin charges. And so this fact actually has a profound consequence, as pointed out by these papers. So if you have a quantum field theory which admits some non-trivial S matrix with higher spin charges, then the S matrix of this theory actually has a nice factorization property. More precisely, if you consider, for example, 3 to 3 scattering amplitudes, like a colliding 3 particle and then collecting 3 particle, and that 3 to 3 S matrix actually can be decomposed into 2 to 2 S matrices. So you actually don't need any more information than 2 to 2 S matrices. And furthermore, there can be different ways of factorizing 3 to 3 S matrices. And those different ways of factorizing 3 to 3 S matrices need to give the same answer. So that imposes some non-trivial relation between different different scattering processes. And that's precisely what people normally call Yang-Baxter equation. So this imposes highly non-trivial constraint on this 2 to 2 S matrix. Okay? And furthermore, what's remarkable is that imposing unitarity and the cross-end symmetry that I already talked about and Yang-Baxter equation, you can almost uniquely determine what is the 2 to 2 S matrix in this theory. So this was done in this famous work by Zamolodchikov. So let me show you the final answer for this S matrix. So to explain the final form of the S matrix Zamolodchikov determined, let me just I need to introduce some notations to explain what the formula means. So the important thing in this theory is that, as I said, the theory in the IR has 3 vacua. And the particles that you scatter, the fundamental particle that you scatter in this theory turn out to be what's called kinks, which is basically excitation interpolating between neighboring vacua. So because of that, basically, if you have a particle trajectory, it's always sandwiched between two different neighboring vacua. So it's kind of like a natural to put these labels of vacua when you describe the scattering process. So here, I introduce a slightly different notation from the previous slides in order to conform with the notation in the literature. So now I'm going to call this vacuum 0, and then the middle vacuum 1/2, and then the third vacuum 1. And in addition, as I already mentioned, the scattering process, the probability of the scattering process, of course, depends on the total energy, which in 2 dimensions is a single variable, which S. And you can people often parameterize this S in this way. So M is the particle, mass of the particle, which is already given. So this theta is a kind of like a change of, is basically what's called rapidity variable, which you can use instead of S. So together with all these labels, now S matrix depends on basically 5 parameters, these A, B, C, D which label vacua, and then theta, which is a parameter which parameterizes total energy. And the cross-section symmetry and unitarity of these S matrices in this notation takes this form. So it turns out in this theta variable, the cross-section symmetry just corresponds to theta going to I pi minus theta. And the unitarity, which basically says the probability is conserved in the scattering process, basically means that this, if you multiply these 2 matrices with argument theta and minus theta, you need to get identity. So this is the unitarity relation. So by imposing crossing, which I already wrote, and then unitarity, and in addition, Yang-Baxter equation. Here, the Yang-Baxter equation also takes a little bit more complicated form because I also need to keep track of the label of the vacua. Then Zamolodchikov basically fixed the S matrix uniquely up to an overall factor, which is not important for my discussion, into this form. So here, it looks complicated, but these D's are basically for some number which depends on the label of the vacua, and then for 0 and 1, it's 1, and then D1/2 is square root of 2. And by the way, this also, I will come back to this point later, but this also coincides with what people normally call quantum dimensions. Okay, so now, as I said, this theory is expected to preserve the Karamas-Wannier symmetry, or Z2 Tambara-Yamagami category. So we expect that this S matrix determined by Zamolodchikov also commutes with the categorical symmetries that are there in this theory. But let me just, before talking about the symmetry, let me just point out that this S matrix, in order to satisfy the cross and symmetry, Zamolodchikov put this a slightly unusual factor, which is the ratio of quantum dimension to the power I theta over 2 pi, and that is going to play an important role in the rest of my talk. Okay, so we do expect that this S matrix commutes with categorical symmetry, but Zamolodchikov didn't check it, so we decided to check it. And it turns out this S matrix, first of all, nicely commutes with the Z2 symmetry, the eta defect. However, it turned out that it actually does not commute with the N defect. So in order for it to commute with the N defect, it needs to satisfy this equation. But you can just take that formula by Zamolodchikov and then check it, and it turns out this is not equal. So now we are facing a paradox. So it seems like the following 4 properties are mutually incompatible. So unitarity and crossing and Yang-Baxter equation, or integrability, which Zamolodchikov used to determine this S matrix. So and if you combine those 3 properties with categorical symmetry that I just talked about, it seems something is going wrong. So we need to give up at least one of the 4 properties. So which one should we give up? Of course, we don't want to give up unitarity, because unitarity is a fundamental property of the theory, which basically means that probability is conserved. What about integrability and crossing symmetry? Categorical symmetry. So these are also rather well established, because you can really check near the conformal field theory point in which you know a lot about this theory. So now it seems like the only viable option, available option right now, is to give up the crossing symmetry. And it turns out, actually, if you give up the crossing symmetry, it's rather easy to find S matrix which satisfy these three properties. And this is the S matrix that satisfies the three properties, which is almost the same as the Zamolodchikov's S matrix. And the only difference is that I just removed this weird slightly weird looking factor by Zamolodchikov. And now it starts to satisfy the commute with the non-invariable symmetry. So it has like all these three properties. However, of course, there is a price to pay. There is a reason why Zamolodchikov wanted to put that factor. That is to realize the crossing symmetry. And now that we remove that factor, now the crossing symmetry, it gets modified. So instead of having like this equals exactly equals to I pi minus theta, now we have an extra prefactor, which is a ratio of quantum dimensions. So far, I only presented our conjecture and then observed that the crossing symmetry is modified in our conjecture. In the rest of my talk, I'm going to explain to you what is the physical origin of this ratio of quantum dimensions and why this modification of crossing symmetry is in some sense natural. Okay? So now let's move on to the derivation. So before explaining the derivation, let me just explain to you what are key physical inputs that go into the derivation of this modified crossing. So the first important property is what I already, the first important property is that in this theory, particles are basically kinks interpolating between different vacua or neighboring vacua. And in the low energy, which is described by topological quantum field theory, the action of a kink on the vacua can be identified with the action of the symmetry line, which in this case, this n-line defect. So let me just explain to you a bit more precisely like what I mean by this. As I said, the particle here are basically always interpolate neighboring vacua. So if you start from 0, you can go to 1/2. Or if you can start from 1/2, you can go either to 0 or 1. So this must remind you something. This is actually exactly the same as the action of the symmetry line n on the vacua. So if you act n on 0, then you get 1/2. But if you act n on 1/2, you can get either 0 or 1. So to put it another way, like you can identify the world line of the particle as the symmetry line of n. And a second important input that goes into the derivation is that in this theory, the vacua are in one-to-one correspondence with symmetry lines. What I mean by this is that you can identify this 0 vacuum with one trivial line and 1/2 vacuum with n line and 1 line with the eta line. Then the way this symmetry line acts on the vacua is precisely the same as the way you fuse two different symmetry lines. In mathematical language, like this is just saying that like the vacua are in the regular representation of the fusion category. And the third important ingredient that go into the derivation is that all the vacua can be obtained from 0 by acting symmetry line. So you start from 0, and then if you act n, you get 1/2. And if you start from 0, and if you act eta line, because eta line swaps this vacuum and this vacuum, you get this one vacuum. Okay, so those are three important ingredients. So with this, let me start explaining how to derive the modified crossing. But as a warm-up, let me derive the action of the symmetry line using these physical inputs. So let's consider a path integral on a very large disk with boundary condition so that like at infinity, you got a 0 vacuum. And this path integral, you can think of it as computing the norm of the states, like states created by zero vacuum. And let's normalize this path integral to be 1. Okay, so this is just to set the normalization. Now, as I said, other vacua can be obtained by acting symmetry lines on this vacua. So if you want to study the state or norm of the other vacua, I just need to act this line here. So this defines the state, and then this defines the norm. However, these other vacua are actually not correctly normalized precisely because the expectation value of this line, the circular line, is not 1, but it's proportional to the what's called quantum dimension. So if you really want to have the normalized state, then you need to divide by the square root of this quantum dimension. Now, with this notation, I can also derive the matrix element of the symmetry lines between normalized states. So if you want to compute the matrix element of L phi defect on this normalized vacuum state, then basically we just need to consider this network of line and then divide by the normalization of the A state and B state. And using the fusion category, you can also compute this network of line, and then this network of line just gives you the square root of the quantum dimension of the 3 lines times the fusion coefficient, which is a non-negative integer. And you can see that like 2 of these square root factors nicely cancels out because of the normalization, but you are still left with 1 square root. So in order to correctly realize the symmetry action on the states, we need to renormalize this symmetry line L phi by dividing it by the square root of the quantum dimension. Okay? So now, let's consider instead a state with a kink in the middle interpolating A vacua and V vacua. So this is a kind of pictorial, like a network notation of the state here. So this V is the word line of the particle, which can be identified with the symmetry line, as I said earlier. And now, using this picture, and then by completing it into a circle, you can also compute the norm of this state. And if you use the same formula, you get square root of dA, dB, and dV. The same formula here. So here, I'm focusing on a particular case. This fusion coefficient is 1. Now using this notation, you can also compute the matrix element of phi symmetry line on this state, which contains 1 kink. And in particular, we can also normalize these kink states. Okay? So this leads to this normalization factor coming from a denominator and this network of line. So this is a slightly bad way of drawing a network of line, but the important point here is that actually this line V and this line phi are not touching. So in a more proper way of drawing this, I should put this V line outside. And this object, if you view it from the 3D, then it's nothing but a tetrahedron. And it actually computes what's called F symbol, computes for you what's called F symbol in this fusion category. So this basically means that the action matrix element of this symmetry line L phi on these kink states are basically given by F symbol. And earlier I said our new conjectured S matrix commutes with the action of categorical symmetry, but when this is precisely the action of the symmetry line which we used to check that it commutes with the action of the symmetries. Okay? So now let's move on to the derivation of the modified crossing using a similar ingredients. And so this is a 3-line summary of why this crossing symmetry is modified. So I'm going to explain more detail in the next slide. But let me just first give you a summary. So the 3 important physical property that leads to the modification is that the IR dynamics is now described by non-trivial topological quantum field theory, as I said earlier. And the important thing is that it turns out the normalizations of in and out states are corrected by topological quantum field theory. And these corrections turn out to depend on the channel we consider. For example, if you consider scattering process in this way or in this way. And this is basically the basic reason why crossing symmetry is modified. So let me just give you more details. So in order to talk about the modification of crossing symmetry of S matrix, we first need to talk about S matrix. So how do we derive or define S matrix in quantum field theory? So normally, a typical way of defining S matrix from quantum field theory is to use what's called LSZ reduction formulas, which involve computing some correlation functions, doing the Fourier transformation, looking at the residues at the pole. However, in the theory we are interested in, we are scattering kinks interpolating different vacua, but the operator that creates kink in quantum field theory are generically non-local. And it is a bit because of that, it is a bit unclear whether the usual derivation of the LSZ reduction, especially the part in which you do the Fourier transformation and look at the poles of the momentum space correlation function, works in a similar way for these operators. So we decided to kind of like resort to a kind of alternative way of defining S matrix, which also works in the usual quantum field theory, which is actually discussed in one of the textbooks of quantum field theory in chapter 5. And I'm not going to explain to you details about this construction, but the basic idea is that you draw two space-like surfaces, which are separated by time t, and then just take some correlation function in position space, and then do some manipulation. So it still involves some kind of like a Fourier transformation, but the difference from the LSZ reduction is that it does not necessarily require for us to look at the poles of the momentum space correlators. So the details of this is actually not that important. The only important thing is that you can get the S matrix from certain Lorentzian space-time correlation function. So in other words, like this S matrix is given by some analytically continued disk correlators. Okay, so these are like a 2-to-2 S matrix. And however, there is one important thing to take into account. Like in the derivation of the symmetry action, we need to take into account the normalization of the states. So this is for example, like if you cut this here, then you have a state which are described incoming particle, which are given by this network of line, and the state that described outgoing particle is now given by this network of line, and the norms of in states and out states are given by these networks of lines. Okay. So the correct expression for the S matrix should be because for the S matrix to satisfy the usual unitarity condition, we need to normalize the state. So the correct one should be like this disk 4-point function divided by these norms, these networks of lines which compute the norm of the state. Okay? And as you can see, the numerator is just a disk correlation function, and it has a usual crossing symmetry property. However, important point here is the denominator actually depends on whether you view this process in this way or in this way, in the horizontal way. And so the crossing symmetry relates the two pictures which are related by viewing this, which are related by rotating this scattering process by 90 degrees. And that basically changes how you view this diagram, like in this way or this way. So because the numerator depends on the channel we consider, it leads to modified crossing equation, and then the modified crossing, the factor that goes into the modified crossing is precisely given by the square root of these networks of lines. And you can evaluate these networks of line, again, using fusion category, and then that is going to give you precisely the ratio of quantum dimension that we saw earlier. Okay? So this is the physical derivation of the, well, I wouldn't say proof, but this is at least a physical derivation of the modified crossing. Okay, so let's move on to the conclusion. So this is basically one well, two-equation summary of what I just said. So the crossing symmetry gets modified, and the factor that goes into the modified crossing can be computed by fusion category, and it's given by the networks of lines. And so, and the main message is that in series in 1 + 1 dimension, which have categorical symmetries, that often lead to modified crossing symmetry, which were missed in the literature in the past. And physically, it comes from corrections to the norm of in and out states due to topological quantum field theory dynamics, which govern the IR, like a low energy. So today I only looked at, explained one particular example, but there are many other examples, for example, for higher minimum models, and also some other deformation of the tricritical Ising model. Actually, for this model, there was an interesting history, because in the literature there are three mutually disagreeing proposals about what the S matrix of this theory is, and our argument supports the conjecture made by these authors. And I should also mention that a slightly similar modified crossing symmetry was observed in Chern-Simon-Mata theory in 2 + 1 dimension by these authors. But the difference from our case is that in their case, the particles that you are scattering are anion. So it was not too much shocking that it exhibits some weird property. And in particular, anions obey, famously anions have non-trivial braiding. But in our example, the braiding is not important, because it's, first of all, because it's 1 + 1D, and furthermore, topological quantum field theory degrees of freedom is more hidden. So in this theory, you start with the Chern-Simon theory, so it's kind of obvious that there is a non-trivial topological quantum field theory. But in our theory, we just started from a usual tricritical Ising model, which is not necessarily obvious that it's governed by topological quantum field theory in the IR. So let's also talk about the future direction. So one interesting future direction is to use this modified crossing and then ask what are all possible S matrices which satisfy this modified crossing equation, and do some kind of bootstrap analysis. And this is actually what we are doing right now, and we already have some preliminary result for Fibonacci fusion category. So I don't have time to explain the details of this plot, but we found several interesting theories which sits at the cusps of the allowed region, and then those turned out to be interesting integrable field theories. And in particular, doing this analysis for Harger fusion categories seems very interesting, because we don't quite know what is the quantum field theory realizing this fusion category symmetry, although recently there are some proposal by taking the continuum limit of the lattice model. And another interesting direction is to think about higher dimensions, and in particular, in the context of scattering a monopole, scattering fermion electrons against monopole, there are several papers recently which pointed out actually there can be some modification of crossing symmetry. And in particular, these two papers pointed out, if you, in some certain situation, if you scatter electron against monopole, this a solid line is monopole, the final state is given by electron attached to some surface defect. But this picture makes sense in this channel, but if you rotate this 90 degrees, then this picture doesn't quite make sense, because you cannot attach a particle to something in the past. So also here, it is natural to expect that there may be some non-trivial crossing relation, an unusual crossing relation. Finally, I emphasize that the physical reason why crossing is modified is some non-triviality of the low energy degrees of freedom, which in this case was governed by topological quantum field theory. And similar non-trivial low energy degrees of freedom, well, actually more complicated non-trivial degrees of freedom shows up in theories in electromagnetism or gravity, and it's often known as soft effects or IR effects. And maybe it'll be interesting to ask whether we can learn something about gravity and a gauge theory. Okay, let me end here.
Question, please, and comments.
the square root of the quantum dimension looks like a square root of a roof genus correction to de-Broglie charges.
Okay.
And which was argued to be actually a wrong correction, but should be replaced by a gamma class. So is it possible that maybe you don't need square roots, but some kind of gamma function, which upon multiplication by conjugate gamma function gives you quantum dimension?
Okay, that's an interesting question, but I have nothing to say about it. Yeah, that's an interesting question.
Other questions, please?
Is this modification also relevant for, say, the integrable worldsheet theories for strings in ADS5 times S5 or ADS3 times S3 times T4 and so on?
So, okay, for ADS5 times S5, I wouldn't expect so, because like a particle that you're scattering are not really like a King's interpolating different vacua. ADS3 times S3, probably not, but it might be, like maybe for massless modes, like there might be something non-trivial.
Other questions?
Sorry, Shota, just in the context, do you think it might be applicable of some of the Kings that can interpolate in this n equals 2 minimal Liouville models? Can you say something?
Some of the Kings, sorry, could you repeat?
No, I mean like there are this adjacent King interpolation between adjacent vacua in this sine Liouville or super, which is essentially n equals 2 Liouville integrable models.
Well, I guess, actually, like one of the examples we discussed in the paper are sine-Gordon theory. So I do expect like if there is a massive deformation and then there is a nice scattering amplitudes, then there might be some modification.
Yeah, because it would be nice in the context of relation to this Landau-Ginzburg series, which it would be a description. But also maybe unrelated question, but do you know there is a question of this construction of the analytic kind of analytic bootstrap for higher D simplices, like going beyond tetrahedron? Do you think?
Are you talking about like a
D-simplex, like
higher fusion categories?
Yeah, if they are involved there, or you can go beyond
tetrahedron.
tetrahedron.
Certainly, in 1+1D, no, but like maybe, I guess like if you start talking about higher dimensional scattering, then that might play an important role. But
so
we don't quite know at the moment.
So this modified crossing there is not understood at the moment, right?
In higher D, there is this result by Minwala and others, which also uses like a various data of this Chern-Simon theory, but the argument doesn't look quite the same as ours. It's probably important to understand the relation between the two.
I see, because the point was like in this context of Sergei von Stroganov, which is like for a simplex probably, then this crossing is not known, and that would be very important.
Hi, can I ask what other systems you've done these calculations for? In particular, if you've done any for systems with twisted Hilbert spaces?
Okay, yeah, so we do expect that this modification of S matrix affects the spectrum of the like a finite size system with twisted boundary condition. And we can, in principle, study it using what's called thermodynamic Bethe-Ansatz, and the computation is like what we are doing right now.
Thank you.
One thing wasn't completely clear to me. It's very intuitive that your picture with the disk and the lines is a normalization that gives complete crossing symmetry. But is that something that you can really prove, or is it just that intuitively that's the one that should have crossing symmetry?
Right. It's not some. Yeah, I think
the numerator there.
Yeah.
Looks like it has crossing symmetry, but is there a completely crystal clear argument?
Well, I wouldn't say we have a completely clear argument. Yeah, it's more like intuitive level.
It does seem intuitively that it should be the right one.
Other questions or comments? If not, let's thank speaker again. For his very well organized and pedagogical talk. So we resume in 5 minutes. Ты будешь говорить с Мелом? А у тебя там есть презентация?
Just a second. Yes, so this is a forward and backward pointer. At the point that you keep it pressed, you can point wherever you want, it doesn't matter. You can also point there, it works the same, wherever you want. touch the cell, so it charges a little bit.
Okay. I turned it on now. Yes. Can you hear me? Okay.
Unfortunately, we arrived to the last talk of this beautiful conference, and I have pleasure to present Nikita Nekrasov, who will tell us two stories about very interesting things.
Okay, thank you very much. So it's indeed it's a conclusion of extremely interesting and very intense conference. I'm very grateful to the organizers for making this possible and for giving me the opportunity to talk. So because it was a very difficult week, so I'm going to entertain you with two short stories in two dimensions. So for us, strings maths is experimental part of string theory, but I will try to maybe open the window into other branches of theoretical physics which we could use to test our ideas at least. So the first part is Young-Mills theory on origami worldsheets. Let me remind you something which is very simple. It's a two-dimensional gauge theory on conventional worldsheet, which let's say we can take to be a cylinder. So if you view 2D Young-Mills canonically, take the space manifold to be just a circle, then the phase space is the space of electric fields and gauge fields on the circle, and you take a simplex quotient with respect to the action of the gauge group, which is a group of maps of the circle into the group. And the result is the cotangent bundle to the maximal torus of the group divided by the Wald group. And the Hamiltonian, which is the quadratic Casimir evaluated on the electric field, becomes just Laplacian acting on W invariant functions on the maximal torus, also known as class functions. Now, in practice, so how we do that, so there is a moment map, also known as the Gauss law, which says that the electric field, which is a function valued in the Lie algebra on the circle, is covariantly constant. And so its invariants are just constants on the circle. And the part, which is the maximal torus divided by the Wald group, parameterizes the conjugacy classes of the holonomy of the gauge field around the circle. And so these are the only degrees of freedom of our theory. Now, let's generalize this story. So instead of a circle, let's take a general graph. Well, I will take it to be a trivalent graph. So I will distinguish internal vertices, which I want to be trivalent, and the tails, which are one-valent. And so if you parameterize this graph by the number of tails and the number of loops, the Euler characteristics being 1 minus g, I assume it's connected. Then you have 3g minus 3 plus n internal edges and 2g minus 2 plus n internal vertices. And so as part of my data, I want to fix a coadjoint orbit of the group per tail. So if I have n tails, I have n coadjoint orbits. And I'll denote them by O of nu I. So nu I stands for the collection of invariants of the orbit. Now, so we can define the phase space to be the space of piecewise smooth gauge fields and electric fields which don't have to be continuous, so they're allowed to jump at the vertices. But the gauge group I'll take to be a group of continuous maps from the graph to define the dimensional group. And so if you perform the symplectic reduction of that phase space by this gauge group, you'll get a finite dimensional phase space whose dimensionality is twice the dimension of the group times g minus 1 plus the sum of dimensions of the coadjoint orbits, which you fixed. So in this reduction, the moment map consists now of two parts. It has the part which is the covariant derivative of the electric field on the internal parts of the edges, and then for each internal vertex, it's a sum of the limiting values of electric fields from all sides. And so when we perform the reduction, we impose the Gauss law, we set all these quantities to 0. Now, if some of the edges at the vertex happen to be the tail, then the electric field coming from the tail is required to belong to the conjugacy class specified at the tail. Otherwise, it's the same condition. So the claim is that this phase space is a quantum integrable system, and so that's the part which is, it's slightly non-trivial to see it from the get-go, but if you think of this system as kind of the generation of Hitchin system, it would be obvious. So I'm going to present that many Poisson commuting Hamiltonians constructed out of the electric field. So for each internal edge, we can take the values of the invariant polynomials on the Lie algebra evaluated on the electric field, and because of the Gauss law, which says that the electric field is covariantly constant, they will be constants throughout the edge. So you just get a number per edge, and the total number of those things are the rank of the group. Now, for each vertex, we have to work a little bit harder to produce additional that many functions, so d sub k is the degree of the homogeneous invariant polynomial. For SUN, those degrees are 2, 3, 4, up to n. For other groups, they are other numbers, interesting numbers. So what you do, you take 2 out of 3 electric fields which meet at the vertex, and you form the linear combination, like a twistor combination, E1 plus lambda E2. You substitute them into these homogeneous invariant polynomials, and then you expand in lambda. Now, so this is a function. This is a polynomial function of lambda, of which you know 3 values. You know its value at lambda equals to 0, because that's the pk evaluated at the E1 at this h, and that's already accounted for. You know its value at lambda equals to 1, because that's the same thing as minus E3, and that's the conjugacy class here, which you fix by other Hamiltonians. And then when lambda goes to infinity, the limiting term will be pk evaluated at E2, and so that's the third h. So out of dk plus 1 coefficients, which this polynomial contains, you subtract 3 for this reason, and that's what you get from each vertex. And so when you sum up these numbers together, you get precisely the half of the dimension of the phase space. Now, this is not the actual story which I want to present. What I want to present, the new part, so this is very old. This is like 30 years ago. The new part is the geometric interpretation of what this phase space is parameterized. And I will do it for the group SU2. So let's start with a simple case, g equals to 0, which is the case when my graph is actually a tree. The claim is that the points on this phase parameterized are polymers in the 3-dimensional Euclidean space modulo isometry. So what do I mean by a polymer? Well, it's a closed n-gon whose edges are have lengths which are fixed by my coadjoint orbits data. So remember, I had to fix a coadjoint orbit, which for SU2 is just a 2-dimensional sphere per tail. And the data of the coadjoint orbit is just the radius of the sphere. So these are numbers now, nu1, nu2, nu3, and so on. So the electric fields which you get at the edges become just vectors in R3. And the totality of the Gauss law conditions just says that they sum up to 0. So you have a collection of n vectors in 3-dimensional space. The sum is equal to 0, and the lengths are fixed. So you can organize them in this closed chain. And so that's what this space parameterizes, up to overall rotations and translations, of course. So now the graph, this is an example of a tree. So the graph actually gives slightly more data than just the polymer itself. It also gives so there is additional discrete information, which is a partitioning of this polygon into triangles by diagonals. So different graphs with the same number of tails will give me different partitions of this polygon. And the equivalence between these things will be a part of what I'm going to tell later. But so the integrals of motion are Hamiltonians built out of electric field, the trace of E squared. Essentially, they are the squares of the lengths of these diagonals. And so in the time evolution of this gauge system living on that space, the diagonals remain intact, they're integrals of motion. So what changes? The shape of the polymer changes. And how can it change? It changes by changing the dihedral angles between the triangles which are shared by the diagonals. So if you turn on different Hamiltonians corresponding to different edges of the space manifold, you start bending these polygons in all possible ways, allowed by the specific partition by the diagonals. And so the symplectic form, which we descended from by the reduction, is just so d length of the diagonal, wedge d of the dihedral angle at each diagonal. So these are the flows, which are called bending flows because they precisely bend the shape. They were studied in a slightly more general case by this gentleman. And of course, In the context of Teichmüller theory, they're also known as Frenkel-Nielsen flows. So they correspond to, I forgot what they call there. Anyway, so there are, of course, gauge theory. The two-dimensional gauge theory is more than just the time evolution on a fixed space manifold. It also, so pair of pants in the simple case allows for the merging or the splitting of space manifolds. And so it would be nice to generalize this story for general graphs, because we can then fuse and split graphs. And that will give us the origami world sheets. So if you slightly deform this story, so deform the 2D Young-Mills into essentially three-dimensional Chern-Simons theory, then this interpretation of polymers in Euclidean in three-dimensional space remains valid, except that now the ambient space will be curved. It will be either a three-dimensional sphere or three-dimensional Lobachevsky space. And so this parameterization of polygons by diagonals and the dihedral angles was very useful in the beta gauge correspondence. So now, recently, so since I want to bring new physics into the game, these polymers suddenly reappeared in a study of Sasha Migdal's loop equations, which he's proposing for describing decaying turbulence. Sorry, decaying turbulence. I mean, the universe could also be decaying, but it's not his study. So he's writing equations for the averages of the circulations around the loop in the fluid dynamics, and somehow by some kind of Fourier transform in loop space, he arrives at this polygonal loops which follow a certain stochastic process. And because of this symplectic structure, you have a natural measure on the space of these polymers, which might be useful in understanding turbulence. Now, what about the case of the higher genus? So already the case when G was equal to 1, and you have any number of tails, is interesting because that just describes conventional Young-Mills theory with heavy charges. So these tails now are the positions where the heavy quarks are sitting, and so they become time-like Wilson lines. So if you take the simplest case of a single n equals 1, you can compute the Hamiltonian in some gauge where the holonomy of the gauge field around the circle, let's say, is diagonal, and then the electric field has this form you can compute, and the Hamiltonian would describe a motion of a particle on a circle. So that's the maximal torus of my gauge group. But now this particle is subject to a potential. And by the way, that type of Hamiltonians, so locally this is the type of Hamiltonians which you get in analytic Langlands, except that in the work of Kazhdan, Eitingov, and Frenkel, this constant mu has a very special value. And if you make it more general, then the issues of convergence, which I was pestering David about, it becomes much more complicated. But the question is, what is the geometric meaning of the phase space corresponding to these high genus graphs? So we can look at the graph closely at the vertex, at the trivalent vertex. So we see that, again, so it has a trivalent vertex, so it's natural to associate to it a triangle in the three-dimensional space. Now it will be an isosceles triangle, right? So it has two sides which are equal, and the one side which I drew in green is a boundary. Now the question is, where is the room for beta, for the dual variable, which we have because it's a two-dimensional phase space, and what's the role of phi of the holonomy of the gauge field? Sorry, I'm not pressing the right button. So the idea is to go to the universal cover of my graph and associate an infinite polymer to that. So if I just make a deck transformation, introduce another copy of this vertex, so now I have another triangle, and now I can attach them at the angle, at the dihedral angle beta. But it's an infinite process because if I go to the universal cover, then I have an infinite number of copies of these things. So we can make it finite. We can make the resulting polymer finite by introducing a conical deficit defect in R3. And so before you introduce this defect, you just keep attaching these triangles, and so they will form this kind of fan structure. If you look, so if you introduce a deficit angle, which will allow you to actually identify the endpoints of each interval, so that this infinite picture actually collapses to just one edge polymer. So if you look at it from the above, so you see there is some deficit angle, and that angle is precisely the eigenvalue, is the angle phi, which is the eigenvalue of the holonomy, logarithm of the eigenvalue of the holonomy of the gauge field around the circle. So, so you see, so if you introduce the conical defect in the transfer space, so it corresponds to inserting a kind of a cosmic string, then it is possible to have a closed polymer now which consists of a single edge, simply because of the identifications of the sides of the cut. And now, so it may be hard to see what's going on, but so I drew using Mathematica some pictures. Of course, depending on whether the angle phi was rational, phi over 2 pi was rational or irrational, you'll have a nice fan, or you'll have something which will be dense. And so maybe you want to use non-commutative geometry to describe this situation. Now, just as a side remark, and since Volodya is here, so there is a canonical transformation relating the different parameterizations of the phase space. So P phi was the parameterization in terms of the gauge field and electric field, and alpha beta are the Darboux coordinates in which where alpha is the action variable. And so you can run two kinds of flows in this phase space. So one is generated by the electric field, which is the usual flow. And so that's this Sutherland type Hamiltonian. And another flow, which is different, but also possible, is generated by the holonomy of the gauge field around the circle. So that would be its Hamiltonian. And so that flow will now make alpha and beta variable change. And that's called rational Reisner-Schneider model. So in the connection to Chern-Simons theory, which I mentioned, so once electric field of 2D Young-Mills becomes the third component of the gauge field, these two choices correspond to whether you want to, in Chern-Simons theory, you can use Wilson line around one or, so this would correspond to Chern-Simons theory on the torus with puncture, and you can use the Wilson loop around the A cycle as your Hamiltonian, or Wilson loop around the B cycle as your Hamiltonian. So in Chern-Simons case, they would be on equal footing, and the limit to Young-Mills make them look different. Now, what's going on for the general graph? Well, if we examine the formula for the dimension of the phase space, so it's the dimension of the space of closed end bond polymers in R3, which we had before, plus 6 times G. So the G is the number of, is the first beta number of the graph. So how do we interpret that? The interpretation is the following, that we are studying the polymers, but now this affine Euclidean three-dimensional space where my polymers are living is pierced by a collection of G straight cosmic strings. So these cosmic strings define, so they're straight lines. They define a conical deficit. So the value, the amount of the conical angular deficit is one of the parameters. The orientation of the string and actually its position is also, there are also parameters. And there's an additional data, kind of a bead, point-like object sitting on the string, which enters the triangulation of the polymer. So, so this is the picture which we had before, but now, so what with a bit more explanation. So this is the picture on the covering space. In fact, the whole polymer in this example consists of a single edge. So this is this mu. It's just that because of the identifications of space due to the presence of the cosmic string, it's a closed polymer, but it has only one chain. And now there is an additional data, which is the triangulation of this polymer. So there is this vertex, which is the other vertex of a triangle, and it is hidden on the cosmic string. But where exactly it sits on the cosmic string is part of the phase space coordinates. Now, I mentioned earlier that if I just think about the polymer itself, there are many ways of triangulating it. And so these different choices of triangulation correspond to different choices of graphs with the same number of tails. So in the simplest case of this S versus T channel scattering graphs, we're passing from one set of double coordinates to another set of double coordinates, and this is a canonical transformation. So there is a function of the of 6 lengths of the external legs and the 2 diagonals on which you partition the quadrangle. So this is a quadrangle formed by alpha 1, alpha 2, alpha 3, alpha 4, and I'm discussing how to change this parameterization from using the diagonal alpha to cross diagonal alpha tilde. So there is a function of these 6 lengths. So it's a function of the geometry of the tetrahedron, such that its derivative with respect to the length of each of these edges, and by symmetry it's true for any edge, gives you the dihedral angle at this edge. So what is this function? Of course, with the experience with conformal blocks and crossing, you would think it's a volume, but volume is measured in cubical meters, and the length is measured in meters. So if you differentiate the volume with respect to the length, you'll get something of dimensionality of the area. And we want the angle. Angle is dimensionless. So it should be a function of dimensionality 1. Incidentally, if you ask the same question in hyperbolic space, the answer would be a volume. But there you have the measure of length given by the curvature, radius of curvature. So if you take the hyperbolic volume and expand it in the inverse curvature radius, you need to go to the third term in expansion to obtain the function which I will go into write. The function is actually very simple. It's precisely the sum over all edges, the length of the edge times the dihedral angle. So there is a formula from ancient times which gives you this angle. It's not Heron formula, but it's a Shapley formula, I think, maybe. And the claim is that if I take this function and differentiate with respect to each of these lengths, side lengths, I will get the corresponding angle. And so when you look at this function, you can't not to notice that it reminds you the celebrated Dane invariant, which tells you whether a 3-dimensional polytope can be chopped up in pieces and rearranged in some other way to give another polytope. So it's a second invariant in Euclidean space, apart from the volume, which distinguishes whether two polytopes are congruent. Now, of course, there is a difference because the Dane's invariant takes values in this complicated ring, and this is just a number. And so this is much more multi-valued than the Dane invariant, but it's OK, because generating functions of canonical transformations are in general multi-valued. Now, to conclude this part, you actually don't need tails at all. So you could have a graph which is, let's say, genus 2 graph, has no tails. And so if you try to draw a so it will be a polymer without any chains, but it consists entirely of the internal triangulations. And so you just start with a triangle with sides alpha 1, alpha 2, alpha 3, and then start attaching to it equal triangles bent at different angles. And so that way you will kind of tessellate a very interesting carpet, which will nevertheless, if you embed this in a space which has cosmic strings. So you start with 2 cosmic strings at with some deficit angles. And now what happens, of course, if you understand the fundamental group of this graph, which is the free group with two generators, is that when you look at one cosmic string through another cosmic string, you will see the third one, and it will start generating an infinite number of cosmic strings because because the monogemies, the associated monogemies of the SU2 gauge field on this graph do not commute, and so it's an interesting space in which to live. So polymers without any edges can live there with interesting dynamics. So there are interesting developments, which I'm not going to present, which is to characterize the class of two-dimensional wall sheets on which this is a meaningful theory. So one can call them origami or foamy wall sheets. So they will contain, they are not smooth two-dimensional manifolds, but they're piecewise smooth. And so they contain, so locally they would look like stars, the three-pronged stars times R, and there are conditions on how you can compatibly glue them together. So these duality transformations can be implemented in this origami wall sheet. So you start your dynamics with something which looks like that across time, and then eventually this edge can shrink, and then the dual edge can start growing. So again, it's a bit of a challenge to draw this in a way which you can sort of appreciate. So I try to rotate this picture from, well, I apologize. It's maybe not so easy. It's, I don't know how to put movies in the presentation. In mathematics, you can rotate it yourself. It's a very simple thing. So gauge theory on this thing, on that manifold will realize this canonical transformation, among other things, which I mentioned. And my speculation, so let's speculate where it's late, that these parameterizations of polymers in 3 dimensions using these diagonals and angles might be useful in the study of QCD string for the 3-dimensional angles. The reason I mentioned Dubovsky et al. Is that in their proposal, the QCD string contains not just the degrees of freedom corresponding to transverse oscillations, but there is this weird axion field, which is kind of massive field, and maybe it can be generated here by taking into account these loops on graphs. Okay, so how am I doing in time? So now on something not completely different, but nevertheless different. So this is a part which is done together with my student, Vasily Yugov, thank you. 2-dimensional gauge theory and twisted bilayered graphene. So if AI were to write this part of the talk, you could have blamed it that it got confused because we were talking about twisted gauge theory a lot in this conference, and but here it's graphene which is twisted, not the gauge theory. So what is a twisted graphene? So what is graphene? Graphene is a monolayered sheet of carbon forming a hexagonal lattice. And Game and Novoselov, who were making them by playing with the pencils, they also produced not only monolayers, but also bilayered, triple layered, and several sheets. And then people were studying what happens with these structures when you rotate one versus another. So it's so of course they form the so-called moire patterns. This is not specific to graphene. These moire patterns we see everywhere. But it was reported that the twisted bilayered graphene has interesting properties at certain angles of this relative rotation. In particular, superconductivity was mentioned. And so people study the system. I don't know if you can see from this slide, but you see there is a kind of an emergent periodicity. So this is the, so there is some small atomic scale, interatomic scale, and then there is a kind of macroscopic scale, which is much larger if the twist angle is small. And so it was reported that if this angle is like 1.1 degree, this system is superconducting. So people proposed models explaining that, notably Bistritzer and MacDonald. And so, of course, I'm not a condensed matter physicist. I can only admire these people who come up with the models for something which is infinitely complicated as condensed matter systems. Nevertheless, by listening to these people, eventually I could identify some pattern which I think we could be of some use. And so people came up gradually to simpler and simpler models of, at least for the Hamiltonian, describing the one particle propagation in this background. And so first people came up with a Dirac operator, and then, well, now 5 years ago, Ternopolsky, Kryuchkov, Vishwanath argued that there is a limit in which you neglect the so-called AA couplings. So if you have two graphene sheets, there are two kind of low energy configurations if you consider them in parallel. There's AA when carbon of the first sheet sits on top of the carbon of the second sheet, and AB when the carbon of the second sheet sits in the middle of the hexagon formed by the carbons of the first sheet. So this is called the AB. And AB is energetically more favorable. So just like if you were trying to pack spheres, you would pack spheres between other spheres. So if you neglect the interlayer AA coupling, this gentleman argued that you get essentially the chiral Dirac operator, which is coupled to an SU2 gauge field. So it's an SU2, the SU2 structure is because you have two sheets. So the electron can hop between two sheets. And so the Hamiltonian contains amplitudes for hopping from one sheet to another. And so we land into our favorite problem of a two-dimensional gauge fields, two-dimensional gauge fields of which we only look at the 0-1 component, just like in David-Stock, for example. Except that now the question is, and it was observed that, I think numerically, that at magic values of the twist angle, which enters as a parameter, so this angle is hidden in this gauge field, in the component of the connection, this Hamiltonian has 0 modes for any value of the quasi-momentum. So it's called flat band. So there is a...
Why can't I just absorb alpha into U?
Nothing. I'll use just some specific double periodic potential. You don't vary it. Alpha is what you can vary. So alpha is what you vary in your lab. Right. So you have a 0 mode for any value of quasi-momentum. So quasi-momentum is essentially a choice of a line bundle. You want line bundle, so you can twist the wave function of electron by something which is quasi-periodic. And it's surprising that you have that. The reason it's surprising, okay, we'll see it later. And so there are proposals that relate the emergence of these flat bands to superconductivity. People say that because of that, electrons can strongly interact, and maybe there is some condensation or something like that. So the question is, what keeps this? What stabilizes these flat bands? Is it a topological phenomenon, or what's going on? So what we will propose is a kind of a geometric picture explaining the emergence of these magic angles, and also give a numerical algorithm for computing the corresponding wave functions. So, of course, we are familiar with Landau problem on, let's say, on two-dimensional torus. We know that if you had the U1 connection, and the curvature of this connection was non-trivial, the first-term class of the bundle was non-trivial, then the index theorem tells you that either the Dirac operator or its conjugate will have 0 modes, and so that will guarantee the existence of 0 modes simply by the topology. Index theorem. But in our story, we have an SU2 gauge field, so the index is identically 0 because we're also in the flat torus. So it means that the existence of 0 modes and the associated flat bands is non-generic. It's something which can happen in the family, but not if you just throw a dice and do things. The question is, okay, if it happens in the family, how many parameters do I need to fine-tune to arrive at this special SU2 gauge field, which will have a 0 mode? So the hint comes from the following considerations, that if my gauge field A sub z bar, which is what we see in this Dirac operator, is such that we have a 0 mode, if I perform a complex gauge transformation, I will also have a zero mode because it's a problem on two-dimensional torus, the fundamental domain of this Moire lattice. So it's a question about the gauge GC orbit, the complexified gauge field orbit of my gauge field. Now, in the case of a twisted bilayered graphene, the elliptic curve on which we're actually doing this story is special. It's it has this model parameter is it's a orbifold point on the module space of genus 1 curves, so it's a cubic root of -1. But let's start with remarks valid for general tau. Now, let me remind you, of course, you don't need this reminder because already we had a lecture by David, for example. If we were to do conventional three-dimensional Chern-Simons theory with compact gauge group on sigma cross R, the states of Chern-Simons theory would be conformal blocks of the level K current algebra. And we can describe them as functionals of the gauge field, of the 0-1 component of the gauge field. Sorry for the typo, obeying that property that if I perform the gauge transformation on this function on the gauge field, this functional transforms with the cocycle. So it's another way of saying that. Yes, that was so that was missing. So it's another way of saying that these are sections of a line bundle, and this line bundle over the modular space of G bundles has level K. Now, there are gauge fields and gauge fields. There are different types of GC orbits of gauge fields, and there is a notion of stability which will play a role now. So there is an algebraic geometric definition of stability saying that for given K, let's say I fix some K positive, there exists a psi, so there is a conformal block. In other words, there is psi which solves this equation such that it does not vanish on this specific representative of the gauge field. So that's a stability. Now, in differential geometry, so as you probably have guessed from the questions I was asking today, I don't like algebraic geometric stability. I like differential geometric stability. So in differential geometry, there is an equivalent way of phrasing it. It says that you can find gauge transformation, complex gauge transformation, such that the curvature of the associated unitary connection will be 0. In other words, you can endow the holomorphic bundle, which is defined by A sub z bar, with the Hermitian metric such that the associated connection unitary connection is flat. So that's why usually when we talk about Chern-Simons theory, we talk about unitary flat connections. Now, if you think about conformal blocks as representing something like partition functions of free fermions, if your gauge field A sub z bar is such that the Dirac operator has a 0 mode, then the associated fermionic path integral will vanish. And so that means that I'm looking for the gauge field for which all the conformal blocks actually vanish on this gauge field. And that means that the associated orbit is not stable. So for the twisted graphene, we need unstable orbits. That's the point. So how to think about unstable orbits? The way to do it is to think about the Yang-Mills flow. So take a unitary connection, and now think of it as of a point in some infinite dimensional space. On this space, we have the Yang-Mills functional, and we can now run the gradient flow generated by this function. So when you look at what this flow does, well, it changes the gauge field by the Yang-Mills equation, maybe by some compensating gauge transformation. And so if you look at it closely, you see that it actually does so by performing a complex gauge transformation on the gauge field. So during the flow, you stay within the GC orbit. The value of the Yang-Mills action decreases, and that's a good thing to have. So just before we go back to gauge fields, let me just give you a simple analogy. If you replace the space of gauge fields by just vector space, the group of unitary gauge transformations by U1, which acts by phase rotation, the analog of the curvature would be the moment map for this action, and the analog of the level k conformal block will be just a homogeneous degree k polynomial in these variables. And so stability in this case simply means that there is a homogeneous polynomial of positive degree which doesn't vanish on z, which means that z is just non-zero. And differential geometric stability means that you can rescale your variables, so act by complexified Gaussian summations, such that the moment map will vanish. And so you can solve for the flow here explicitly, and you will see that if your point z is equal to 0, it stays at 0. But if it's non-zero, it will get attracted to a sphere, to the 2n minus 1 dimensional sphere. And then if you quotient by u1, you'll get Cpn minus 1, which is the analog of the modular space of stable bundles. So we have two critical points. The one where which corresponds to absolute minima of the function f squared, which corresponds to a sphere, and then the one when z equals to 0, the unstable point with the high critical value of the associated function. So back to Young-Mills theory, the study of critical points and gradient flows there has a rich history, going back to IT Abbott. And so the picture which I want you to keep in mind is the following. So there are flows which take most of gauge fields by the flow will be brought down to the space of flat connections. So you just, curvature goes to 0. But there are certain gauge fields which get stuck at a high critical point. So what are these high critical points? These are the points where so you have a solution of Young-Mills equation, which can, in 2 dimensions, have a simple form. They say that the scalar, which you get out of the curvature by taking Hodge star, is covariantly constant. And so if the connection is not flat, it means that the scalar is non-zero, which means that the connection is reducible. So your structure group is reduced to the commutant of that phi. And for simplicity, so for gauge group SUN, there are intricate patterns of this breaking, but let me focus on simplest ones for which this field can be, this phi can be diagonalized with distinct eigenvalues. Then, if you recall that phis are actually curvatures of, they actually become the curvatures of the abelian connections on which your gauge field splits. So the values should be quantized because of the flux quantization. And so if you arrive at such a solution of Young-Mills equation, your Young-Mills action will be strictly positive and proportional to sums of squares of the fluxes. So now, every such solution comes with a family of, we can call them marginal deformations, which don't change the value of the Young-Mills action. Namely, you can shift the abelian Young-Mills connection by flat connection. And so these flat connections are parameterized by the Jacobian of the Riemann surface. And so you have n-1 copy of such Jacobians for SUN. For SUN, in general, there are other types of solutions. But for SU2, these are the only ones. Now, for elliptic curve. For elliptic curve, yeah. For elliptic curve, it will be just, yeah. Sorry. In general, it's not. In general, it's not. If sigma is elliptic curve, it will be, yeah. But I drew it a torus because the torus was the Jacobian of the curve. In my picture, in this picture, this is the Jacobian. This is to the power. So that's the product of a Jacobian of a higher unit surface. Yeah. Now we are in business because now we've got abelian connections, and because the sum of the fluxes is equal to 0, some of the fluxes will have to be positive. And for those for which whose are positive, the associated Dirac operator will have 0 modes, and those are the flat bands actually. And the fact that you can shift this connection by a flat connection, that explains that you have the flat band for any value of quasi-momentum. So these flat connections are quasi-momentum. So these are desired flat bands. So for SU2, for n equals 2, this is the generic situation. For if you were to study multi-layered, multi-twisted graphene, they could be mixed phases, which I think are worth investigating. And there are interesting connections to work of Friedman, Morgan, Witten, which actually, I don't know if Ed thinks of this that way, but actually they used this, the first critical point to describe the modular space of flat connections. So it's an interesting way to interpret the Lohenga theorem. But let me not go there. So, but we have a puzzle. So the puzzle is a codimension of the space of critical points. So so you see, so you have this locus of high critical points, and there is a certain number of negative directions, so a certain number of deformations which will take you from that locus all the way down to this locus of flat connections. So if you want to fine-tune your initial conditions for the flow, ensuring that you arrive here, it means that you need to impose as many conditions as the dimensionality of the space of negative modes. In the language of RG flows, this would be relevant deformations. And you can compute the number of these negative deformations, and you'll find that there are 3. So there are 4 zero modes, but there is also U1 gauge symmetry, so there are 3 effective directions. So it would appear that we need to tune 3 parameters to arrive at a flat band, whereas the evidence shows that we need only 1 parameter. So what's going on? So this is a discussion of how one computes these directions. So this is algebraic geometric way, and there is again the differential geometric way, simply to compute the negative eigenvalues, directions of the second quadratic form. So first of all, we did verify numerically by taking the formula for the gauge field, which was derived from the Hubbard model, that at the magic values of the angle, by running the flow numerically, we did arrive at the Young-Mills connections. And I mean, the 0th order test is to compute the Young-Mills action on that specific connection and to see that it's strictly higher than the action for the first critical point. So that's a test number 0. But then you actually run the flow, and with the precision which you can get from numerical computations, you do get at this point. But we have, so we have 2 marginal directions and 3 relevant directions. So in principle, it could have been that we need to tune 5 parameters, but we tune only 1. So how is it possible? The answer is that the elliptic curve on which we are working is a special curve. It has a Z3 symmetry, which is descendant from the hexagonal symmetry of the graphene sheet. And it's a good thing that we discussed the connection on a trivial bundle. So if you have a symmetry of base and you have a trivial bundle, then it leads to symmetry of the bundle, and it acts on the space of connections. And so the ansatz of Ternopolsky, Kryuchkov, Fishman is actually Z3 invariant, and the flow commutes with Z3 symmetry. And so so if you look at the way the space of relevant deformations decompose under the action of Z3, you see that they decompose into 2 conjugate non-trivial representations. So modular gauge U1, it leaves you with, I call them mustaches. So these are kind of one real dimensional now lines. You have several of them, but they're one-dimensional, which emanate from this high critical point. And so in the space of Z3 invariant flows, it's now, those things have precisely codimension 1. So that's the explanation. Okay, so then there is some discussion of how the Z3 acts. I'll skip that for lack of time. So this, at least within the model of this gentleman, the emergence of the angles, the fact that it's just one angle is explained by these geometric considerations. So there are possibly interesting directions to investigate. Maybe one can also say something about the more sophisticated graphene sheets, because people now make graphenes, they roll them up, they combine them, they twist them, they can make origami out of them, and so maybe there is some connection to part 1 of this talk. So to conclude, I wanted to mention my mentor, Jan Kogan, who was a great physicist who had an interest in all kinds of branches, all branches of theoretical physics. And so he died last week, 21 years ago, here in Trieste, suddenly, and left a void in my life. So it was thanks to him that I personally got really contaminated with this desire to understand things and to express them in terms of some mathematical formulas. And so I would like to dedicate this to him. Thank you.
Thank you very much for your very inspiring and interesting talk. And I want to say personally that I completely share what Nikita said about Jan. Each time when I'm in Grignano, nearby the hotel Adriatica, I remember a very good friend, Jan, who visited us. Also, we shared ideas. It was a really very good friend and great physicist. Please, questions and comments.
Yes.
So you had this special ZC curve in your because of the lattice. If you have a higher genus curve, would you get a Picard curve?
Would I get, sorry, what?
A Picard curve, one which is sort of given by a triple covering of the plane.
So if you have a if you have a curve with additional symmetry, that is very useful for the analysis of these flows. So you can have special flows which will require fewer parameters to tune. I don't know if you can make a material which will realize that, which will actually realize it, but why not? Maybe, you see, if you take a multi-layer, again, thinking in terms of Hitchin systems, if you take a multi-layered graphene, who knows, maybe there is a spectral curve hiding there of higher genus.
Okay, thank you.
Yes, Greg.
Well, that's related to a question I was trying to understand. So you took sigma to be an elliptic curve, and then it wasn't when you discussed the general Yang-Mills flows, because it makes sense then. But is sigma torus because that's the Brillouin torus?
Yeah.
Oh, okay. So then the higher genus is just a mathematical extension, or are you
maybe.
I mean, sometimes Fermi surfaces can have higher genus, but you know, if you're just doing, you know, band theory, it's going to be a torus.
Right, but we need some kind of. So here it was interesting that you can actually realize a non-abelian gauge field in laboratory. So maybe one can, who knows? I mean, it could be that there is an effective Fermi surface which takes into account this non-abelian structure. Then it could be of high genus.
Other questions, comments, please.
People are tired. Let's thank the organizers for making it bring it up.
It's a pleasure to thank them. Titanic work, really. Thank you very much.
Actually, could I ask the fellow organizers, co-organizers that are here to come up, please? So, yeah, I want to, we've come to the end of what's been, as Nikita mentioned, a very intense week. I wanted to say that, I want to say a few words of thanks. So first of all, I want to thank all of the speakers for an absolutely excellent program of talks. Especially a special thanks to the presenters of the short talks and the posters. And thanks to everyone who chaired
and also to the our students that were running around with the microphones and so on. A big thanks to the co-organizers, Francesco, Giulio, Alessandro, Pavel, Claudio and Lothar, who are not present here. And actually, I personally want to say a special thanks to Agnese, who really did bear a lot of the load. That we had co-sponsors for the meeting, as I mentioned at the beginning, which were CISA and the INFN. And then some thanks to the people and teams at the ICTP, so that's the IT people and audiovisual people, security, housing and reception, the visa office, the operations office, the team at the info point, the transportation team, and from the sort of programs and the finance team, and especially to Victoria, who was the conference administrator. Thank you very much, Victoria, and all the others. And finally, also to the String Math Steering Committee, a couple of whom were here, or maybe still are. I don't see them. And yeah, that's all I wanted to say. Does anyone want to add anything? So, yeah, thank you again, everyone. Yeah, I mean, thanks also to the participants, by the way. I didn't mention you all. Thank you very much for coming. And for those of you that are staying around, enjoy the rest of your stay. And if not, safe and smooth onward travels.
Yeah, definitely. Thank you so much for mentioning of your...
yes, thank you for the reference.
Yeah, please do, yeah. Enjoy.
See you.
Much.